Well, first of all, when you think about the intersection of water and energy, for us in Oklahoma, that's oil and gas activity. That's sort of our bread and butter. We were very used to produced water. That's something we've dealt with now since oil was first discovered in Bartlesville in the late 1800s, right? It's something that we're very accustomed to. There was a step change in that, excuse me, about 20 years ago when unconventional hydraulic fracturing completion activities were really developed here in Oklahoma. It's not a story that maybe gets told as much as it should, but when you look at the combination of horizontal drilling and hydraulic fracturing, Devon Energy really pioneered that in the gas shale play in Barnett Shale, which is north of Dallas in that area, and Continental Resources did it on the oil side in the Bakken Shale, which is up around the border of North Dakota, Montana. And from that, we've really revolutionized energy production in the country, and the geopolitical ramifications of that have been quite profound. So it's been something that really was started. And we take great pride of that here in Oklahoma City, about having this be the nexus of that step change in energy production. We now have former Chesapeake Energy. Expand Energy is the largest natural gas producer in the entire country. Of course, natural gas has become a very big geopolitical benefit to the country. When we look at, we're now the largest natural gas LNG exporter in the world, here in the United States, largely out of the Gulf of. I'll just leave it at the Gulf. I always trip myself up on that every time. Just leave it at the Gulf. So it's really been a profound deal. But when you look at the step change of produced water, with the unconventional completion activity, we had a lot more water that we had to deal with, and we had a taste of that back in 2011. We got our first real up close and personal interaction with that, with a 5.7 magnitude earthquake in Prague, Oklahoma. That really kicked off about an 8-year period or so of really elevated seismic activity and felt seismic activity. And we decided as a state, and at the time I was with Devon Energy, and I was part of a group that led the response, a multidisciplinary response for Devon to how to respond to the earthquake activity we were seeing from produced water largely. And it was really, to me, a lesson in good government policy and cooperation with corporate citizens who were trying to do the right thing. We've gotten to a point now where we're really basically back down to background level seismicity in Oklahoma. So it's really a positive story, I think, in how government and business can interact and with the collaboration of science and figure out how do we reduce this while still having the development and the oil and gas activity that we were accustomed to seeing in Oklahoma. So it's been a success, I think, quite a bit and quite all around. As you're here today, I also want to talk about, we have the National Academy here, and I think it'd be worth mentioning that we're in the Innovation District in Oklahoma, which is sandwiched between downtown Oklahoma and the University of Oklahoma healthcare facility. And it's really an area that's a hub of entrepreneurial activity, of having capital come meet businesses that are growing and starting up. And there are 3 clusters that they've focused on. One is biomedical research, and we have a new facility that you might see just across from where we are now that is an incubator and a hub for largely biomedical facilities, but it'll be other facilities as well. With the OU Health Center right here, that's a burgeoning area we see in the state and in this particular area. The other is aerospace. We have some aerospace. It's probably the 3rd biggest industry we have in Oklahoma now, but the fastest growing. And that is part of one of the clusters that's a focus of the Innovation District as well. And the third, of course, is energy. And we're here today in the Ham Institute building. This was a building that was really formed back in, I think it was 2014, 13, somewhere in that time frame. That was a GE technical center. At the time, they had technical centers around the world for their various areas of operation. This was the oil and gas technical center for the GE operations. And that was largely because of the Devon Continentals, Chesapeake's now Expands of the world, and the innovation they were doing around hydraulic fracturing and unconventional stimulation. And GE decided to locate their headquarters here. And they had a series of corporate restructuring and some acquisitions, that sort of thing. And the opportunity came for Harold Hamm is the founder of Continental, to partner with Oklahoma State University. And he donated through his personal gift and through Continental's gift about $50 million to create the Hamm Institute a couple of years ago to really focus on energy innovation and how we look at innovation going forward. And the Hamm Institute's been a real thought leader in that, with the change in administration in DC and maybe some different priorities there. And they've hosted small roundtables that are really meant to drive policy around a few different things. One is geothermal energy production, and I'll be remiss without saying that if you haven't gotten a tour of the facility yet, you should. There are a couple of test wells just in a lab down that way, whatever direction that is. And there's a 400-foot test well and a 65-foot test well. The 400-foot test well is currently actually testing various geothermal type technologies, and the 65-foot well is used for downhole pumps and things like that they test too. So that's something that's happening right here in Oklahoma, just 100 yards down the hall there. But geothermal has been one of their areas. Nuclear has been another one of the areas they're focused on. And how do we develop good policy around nuclear? And then the third is natural gas. And so they've had small groups on each of those three topics. They're now rolling those up. They're going to several different cities. They'll be in DC in a couple of weeks, and other cities around the country to kind of give some lessons learned on those small groups, get more feedback, with the hope of having some policy recommendations that come out around those three areas of energy production going forward. But of course, we're here to talk about water, and produced water is more my background. I know a little bit about that. Prior to being Secretary of Energy, I was the chief legal and administrative officer for a water midstream company, Lagoon Water Midstream, which had several hundred miles of pipe, a couple of dozen disposal wells in two basins, one here in Oklahoma and the other out in the Permian Basin, around Midland Basin. And as I thought about produced water and kind of the lessons learned from that exercise, we sold the company. We're private equity backed. We sold the company in late last summer, which created the opportunity I'm currently in now. But as I was kind of thinking back about lessons learned, there are basin specific ways of looking at how you use produced water. And for instance, we had in Oklahoma, I think anyway, nobody's ever proven me wrong in this, the first commercial recycling facility in the state of Oklahoma. It was here. But Oklahoma's the use of produced water to recycle it. And when I say recycle, that means they use it for stimulation activities and the oil and gas activity to complete wells, to fracture wells, that sort of thing, was kind of new. And to have produced water used in those kind of activities, it had to be highly treated, highly it's settled, get all the particles out of it and that sort of thing. And then even then they blend it with just a very little bit of produced water and a whole lot of fresh water to complete their wells. And then our lessons were different when we went to Midland Basin. Of course, there are water scarcity issues there that are different, but they would take produced water right off our pipelines and send it straight to their completion activities, spike it with some chemicals, and it'd go right down hole. And they would use a lot of produced water and a little bit of fresh water in their completion activities. And so there was really basin dependent. And that's a lot, some of the geology affects that, but it's a lot of just the comfort level of the various engineers that are behind those activities. They will have specific engineers on one basin that are different than the ones in the other. And it's a lot of lessons learned that they learn internally on how to fracture wells and complete wells and handle produced water. And the other things we learned is when engaging the companies, each company treats it a little bit differently too. And there's no standard playbook for that. And in some companies you go to, it'd be a completion engineer that was in charge of all their water. And others would be a production engineer that dealt with it after the well was completed, and they just had to get water as a waste product. They just want to get rid of it. And they were in charge of it all. And then other companies were their midstream arm, where oil and gas comes out of the well. They would just add a third line to that of produced water and deal with it all together. And so it was a hard thing to kind of figure out. There's no playbook on that, but each company deals with it a little bit differently. And so that's when you're talking with companies and taking lessons learned and the sciences learned for produced water and water use generally, that's a challenge to overcome as well. But taking forward in the use of oil field water, to me, there are really three main challenges that I'm sure is highlighted as a focus here. But one is just reducing the amount of fresh water used and oil field activities. And that example of Oklahoma and Midland Basin is kind of telling on that, right? How do you reduce fresh water and get more comfort level around recycled water, recycled produced water when completing wells? The other is beneficial reuse of the water. And somebody, I forget exactly who, somebody touched on that. I think it was the Devon, from Devon's in charge of beneficial reuse there, but not only in the oil field services context, but also in industrial applications for cooling towers or whatever it may be. How do we, and ideally the golden, the golden ticket is getting to the point where you can have surface discharge at some point. It's not economic now, and there's a discomfort level generally around that, but that's ultimately I think should be a goal of what we do with produced water in the oil field service or oil field activities, especially considering that a lot of oil and gas activities line up perfectly with areas that have water scarcity, freshwater scarcity, right? So there's certainly a natural synergy there. And the third is mineral extraction from the produced water itself, right? We've heard about it, and there's some comfort level around iodine. We've seen that around lithium, especially with the Smack River Formation in Arkansas. But there's a lot of other stuff in that produced water stream as well. And how do you harness that and and this is really also an intersection, not only technology, but policy too, because there are some policy restrictions around the states, various, depends state to state. But how do you get those to align such that we can maximize those resources and extract economically what's in the produced water, especially when you look at the push that we have from a national security effort around rare earth minerals and those type of things. There's a scarcity of those. There's not enough of that kind of thing. And how do we extract what we have from the produced water and make that useful going forward? So that's kind of, as I was kind of thinking back about produced water context, of course, the intersection of energy and water is a little bit broader than that, but I wanted to touch on that. And those were my lessons learned, and glad to be here today. And I look forward to seeing all you guys at the game tonight.
Thank you very much.
Thank you.
Thanks for joining us. I know we have online Charles Scaife, and I didn't know whether you wanted to provide a few words.
Yeah, thank you so much. And thank you for those remarks, Jeff Starling. Those are really great to hear. I'll be super brief here and just want to really welcome everyone. I know I'm excited to learn about some of the energy water nexus issues and conversations in this region. I also want to point out that there's a lot of us from DOE on the call, as you all heard in the introductions, and then at least one of us in the room, Tashara Gunda, who will also be participating. Hi, Tashara. Good to see you. And that will probably have one other person joining who lives down the street in Tulsa. So really looking forward to the conversation today. And yeah, thanks again, everyone.
Thanks for joining us and for all your support. I think we're going to transition now to the next show. I think there's probably very few people in this room who don't know Nick, but Nick is in charge of our next panel, and go for it.
Yeah, you bet. So our first panel discussion today is going to be non-traditional water supplies from and for energy production. And we have three excellent speakers to get us started on this topic. Shelley Shard, Rick McCurdy, and Eric Bernard. I've known Shelley and Rick for a long time. I just met Eric this morning, but I'm looking forward to hearing what he has to say as well. The way we're going to do this, the speakers are comfortable. You can just stay at your seat and talk if you want to, or you can go up there. It's whatever you're comfortable with. But we're going to hold questions and discussion until after all three speakers, and then we'll have Q&A and discussion time.
Okay, I think I'm going to go up there so I can see everybody instead of seeing a few of them. Okay. So
You are up, yeah.
okay, there we go. So good morning, everyone. As Nick said, I'm Shelley Chard. I'm the Water Quality Director at Oklahoma DEQ. It's great to have all of you here with us in Oklahoma City. I just want to kind of give you a little bit of background on kind of who Oklahoma is in terms of water and energy, and, talk a little bit about maybe a new book for the future. You wanna go ahead and advance for me? Okay, so, this is the map of Oklahoma. Those of you who are familiar with the state, you know, we may be dealing with extreme drought, extreme flooding at the same time. And this impacts everything that we do. Out in Kenton, Oklahoma, if we get a foot of rain in a year, we're doing great. You go to Mount Herman, down southeast Oklahoma, we may get over 60 inches of rain. And those will happen in the same year. And we still have an agriculture industry that is big here. We still have oil and gas that needs water. We have hydroelectric power that obviously needs water. So what do we do and how do we deal with this? If you will, the 98th meridian, that's the other one that's important for those of you who deal with oil and gas produced water. Can we discharge? Can we even consider discharge? We have to have that that distinction. EPA made the decision that if you were west of the 98th meridian, you could discharge if you could meet limits. So the limit that they set, good enough quality to support livestock or wildlife. Okay, no other program does EPA talk about good enough quality. They tell us what it is and how we have to meet it, when to meet it, where to meet it. So this is a weird one. So this part of the state is considered arid west, which is why we can have that discharge. Anybody know why it's the 98th meridian and not the 100th meridian, which is really the official climate delineation? Not seeing any. You may have heard of a person named Lyndon Johnson. He had a ranch. And they did a lot of oil and gas exploration and production. He needed a discharge. So the line was set at the 98th meridian. So if you're in Oklahoma, in Canadian County, in the city of El Reno, if you are on the west side of the municipal airport, you can discharge. If you're on the east side of the oil and gas wells, on the east side of the municipal airport, you can't. So that's a little arbitrary. So that's something that maybe we need to think about or talk about. You'll go ahead. I mentioned we may do drought flooding at the same time. This is an old map. This is 2012, but it highlights, we see this every summer. It's just a matter of which shade of dark red are we. So we had to start thinking about what are we going to do to support all of the industry, our outdoor way of life. But oil and gas exploration production, as we all know, is water intensive. It's a matter of how do we deal with the water? Where does it come from? How many times do we reuse it? So because we were having these issues, go ahead. In 2012, there was a bill that passed the Oklahoma legislature. It became known as Water for 2060. It says that Oklahoma will use no more fresh water in 2060 than in 2010. And we will continue to have economic development. We will continue to protect public health through adequate quantity and quality of drinking water. We're going to continue to hunt and to fish and recreate at our lakes. So how do we do that? So the part you care about in Water for 2060, this is when we really started looking at produced water. Not just, oh, how fast can we get rid of it? Where's the closest injection well? Started really looking at, can we treat it and reuse it? If so, for what? Looking at what we have termed marginal quality water, primarily saline groundwater. And you don't know a lot about Oklahoma drinking water. A lot of times our groundwater that technically meets US drinking water standards is actually more saline than some produced water. In some states, the coal bed methane in Wyoming is significantly higher quality than a lot of our groundwater. So we're looking at how do we use this marginal quality groundwater. Water loss reduction, we talk a lot about that in terms of drinking water systems, treated water. But how many of you have seen lay flat pipe that's looking like silt? That happens in any place that is a permanent or temporary conveyance of water. And then water recycling and reuse. This was an area that we really started looking at for our municipal uses, our drinking water uses, but more importantly, looking at fit for purpose use. And that's where produced water comes in. I don't think any of us expect to be drinking produced water that has been treated anytime soon based on the amount of contaminants and the high concentration of salt, particularly here in Oklahoma. We will see produced water up as high as 300,000 parts per million. That's the problem. You can't, we calculated, I think we would need 17 new landfills every year if we treated produced water down to a usable for a municipal purpose. So those are things that we've been trying to work through. Next slide. So just some quick energy facts. I know Secretary Starling touched on some of this a little bit, but Oklahoma produces 3 times more energy than we consume. So we're sharing our energy with our state partners. We are the 6th largest producer of gas and crude oil in the US. We have 5 refineries producing over 500,000 barrels per day. Every day they run 24 hours continuously. We have about 3% of the refining capacity. We have about we are 6th in the reserves for natural gas. 14% of crude oil in the United States is stored in Cushing, Oklahoma. You're about, I don't know, hour and a half, depending on the roads. After the floods, it could be a week from here. So we definitely, you know, always joke, we're the center of the universe. Of course we are. We have all of the crude oil storage is here. Like I said, 14% for the country. Cushing, Oklahoma is where intermediate Texas crude prices are set. That's also kind of a random thing that people don't necessarily know. And 4% of the energy we produce is hydroelectric. That's also something that's like, hey, remember that map and all of the red? That's a problem. But we do have in eastern Oklahoma a whole series of hydroelectric dams for the Red River Dam Authority. So circular water economy. Go ahead. When we look at economic development, you gotta have 2 things. You gotta have water and you gotta have power of some sort. Basically, it all comes down to how do you encourage economic development, employment opportunities. If you have all the jobs in the world, the quality of life is horrible, people aren't going to stick around. So that again brings in all of the water aspects of what we do and how we do it. If you have an appropriate water supply, quantity and quality, and you have the ability to maintain your electric power, you can do a lot of things. We don't generally spend time worried about, oh, it's 100 degrees. Are we going to have a blackout? What's going to happen? We hear that in some parts of the country, but we don't. So that, you know, increases the quality of life and people sticking around, companies coming in, expanding, and providing additional opportunities. Agriculture is a big one. We produce a lot of ag products here in Oklahoma. They take a lot of water. You know, we think about, you know, growing wheat. Well, there's not just the growing, but we've got to harvest that. We have the power that generates all of the farm equipment, whether it's gas or electric. We also have all of the water that it takes to build and create those equipment that's used. Just some statistics, you know, the US, we produce, we're the fourth largest producer of wheat, second largest beef producer. If you're gonna be here more than a day or two, highly recommend going out to Stockyard City, USA. The great steaks in the state because it's right next door to stockyards. Chickens, we're the 12th largest producer of poultry and the 6th largest producer of pork. And most of that pork that's produced is out in the panhandle where they get a foot of rain a year. Energy costs associated with water treatment distribution. This is again an opportunity where we come back together. It takes a lot of energy just to distribute water, to put it where it's needed, whether it's raw water, that fresh water that hasn't been treated, if it's treated to drinking water standards, or somewhere in between that fit for purpose water. When we look across the world, 2 to 6% of all electricity goes to the treating of water. And when you think about that, how many countries don't have water that they're treating, you know, so some of us are spending really a lot of electricity to produce that treated water. Treatment technologies and source water quality obviously drive that. How far you have to pump it is going to affect. Lots of overlap in water energy. So we have to kind of figure out what we're gonna do and how we're gonna maintain our way of life, particularly for those of us that have legislative mandates. One more. Great. Okay. So first I will tell you, this is a real picture. It was taken by one of my staff in Durant, Oklahoma, for those of you from around here. Pulling out of Walmart in a small town. And so it's like, okay, kind of funny, but what's the point? Well, we have to be innovative. We have to figure out this cost of treating water, this cost of producing additional energy, whether it be oil and gas, whether it be hydro, whether it be wind, whatever it is. It doesn't magically appear. We're spending money in order to make it. Well, if we keep doing what we've always done, we'll keep having what we've always had. But this is an example of, okay, Grady needs to go to Walmart. I don't know why, but you know, maybe it's groceries, maybe it's household goods, whatever it is. Well, obviously, we don't have a car because surely if we had one, that's what we would drive. It's hard to see, but if you look, you know, safety first, Granny is strapped down. She had, the chair is tied down and there is a cord around her. You can see down toward the bottom by her feet, there are bags. They are strapped down. Bubba, he's got his yellow and kind of faded red flags notifying people I'm a slow moving vehicle, be careful around me. But if they can come up with this to get what they need from Walmart or any place else, surely the great minds of our country, we can solve some of these issues of how do we do this differently? How do we treat water more economically? How do we move water? How do we stop having to move water? How can we treat these marginal quality waters, these industrial produced wastewaters, produced water in order to keep us moving in the right direction and keep energy flowing the way that we need it. So with that, Nick, I will turn it back over to you.
Thank you. Discussion until after all three speakers. Eric, you're up next. Eric Denard from Texas Tech University.
Good morning, and thank you all for the opportunity to be here today. I'm going to present kind of an overview of what the Texas Produced Water Consortium has been up to. And we really thank Pay and the group from New Mexico Produced Water Research Consortium. They had about a 2-year head start over us in this game. And maybe the slides will advance. Here we go. So the Texas Produced Water Consortium was created by Senate Bill 601 in 2021. And we have a wide, diverse membership of folks that is representative of all of the major kind of players in industry, from upstreams to midstreams and producing companies, and then environmental groups, and then all the agencies at the same time that are part of us. Senate Bill 601 housed the consortium at Texas Tech and operates with really 4 kind of distinct groups that interact all the time together. Our membership early on told us to focus on hydraulic fracturing and unconventional production as compared to other things. And all of that, tends to find an epicenter in the Permian Basin. So as we've looked at this kind of process over time and thought about, where it's effective and where it's challenging, when we first started the process, the potential beneficial uses identified were the things down the right-hand column here, where we looked at oil and gas production reuse, and industry kind of not oil and gas use. Construction was talked about a lot. Down at the very bottom of the list, you see things like groundwater ASR and surface water discharge. We'll come back to those in a little bit, but now those are kind of moving to the top of the list. So those are important priorities. We've also worked a lot on understanding the technologies that are available to us and the terminologies that are used to describe what is produced water. That turns out to be a challenge, as we've discovered in the last 12 to 18 months. One of the things about produced water in the Permian Basin is it comes from primarily these 2 basins, the Delaware Basin on the left in the red, and the Permian Midland Basin on the right in the yellow color. That water is typically around 170,000 TDS right now. Seawater as a kind of a benchmark for desalinization is 35,000 TDS. So we're about 4.8 times the TDS levels of seawater. So desalinization is really challenging. When you think about what that means to things like metallurgy and how long a product can last, those are really important considerations. We've learned a tremendous amount, even in recent time, about different kinds of pipe infrastructures and coatings and things, and what happens under certain chemical compositions to those, kind of materials. A really important set of considerations there. We look at a lot of now produced water as a whole, how much. Right now, our current kind of estimates are about 27 million barrels a day between New Mexico and Texas. New Mexico ships 2 million barrels a day over the border into Texas. That means we go from 23 to 25 million barrels a day on average. Right now, all of our partners and members estimate that we can recover about 50% of the total volume of water. That means that we're talking about somewhere in the neighborhood of 12.5 million barrels a day, 1,600 acre feet, or about 525 million gallons a day. As a benchmark, that would be 5 El Pasos worth of water per day that we could potentially desalinate. So if you think about, what this means in the volumes, sometimes those numbers don't necessarily get there for us. So another way to think about it is that's 22,000 rail cars a day. That's a number that's just not even available in the United States right now. That's 7.6 million a year, circle the globe about 3.5 times on an annual basis. Build the capital 11 times a day or 4,000 times a year in the state of Texas. So that's the side of it, that's the produced water side that could be desalinated. So treated for some beneficial use outside of oil and gas. What also comes with it though is waste. And it's about a half, so about 50% recovery rate. That's about 39,000 rail hoppers a day or gondola cars a day. About 14.5 million of those a year, 5.7 times the globe in terms of what that would look like. That's a tremendous amount of salt primarily that is just, there's no way to dispose of that on a continual basis. So the 50% recovery rate really gets us, to some conversations about the energy that's used to consume it. So if we started off with raw produced water at 170,000 TDS right now, typically we'll pre-treat that water. The methods then involve some small amount of energy in this case. That's usually starting with sand filters and oxidation processes like DAF and peroxide ozonation, filtration things, flocculation, absorption, electrocoag, and then stage precip. That's going to get us to something that's called in the oil field treated produced water. But that's not what we're thinking of as treated produced water for beneficial use. So this last year, we went through a very specific set of exercises to come up with this set of terms that you see on this slide for what each one of these product points really entails. None of the literature or the administrative code aligns with this currently, and we really hope it will soon to solve some problems. So what was happening is the New Mexico and Texas Produced Water Consortiums now collaborate on water sampling and testing. We send that off to a third-party lab. The third-party lab was getting samples that were denoted as treated produced water that were actually clean brine that's still 120,000 TDS water that then fouls an instrument and requires a complete recalibration. That doesn't really work there. So when you think about what pre-treatment gets us, we're really dropping to 120,000 TDS. When we then take on a desal step, there's a series of different thermal processes that typically are used for water that's this high in TDS. You can usually get down to 120 to 140,000 TDS water and then use membrane technologies. So there's different companies that are testing out a variety of these different technologies. New Mexico has done a lot of work with bench scale technologies and understanding what that scale's like. Our membership said, don't replicate that. Wait until you get to smaller scale commercial pilots and then start to test those. So we're not duplicating effort. So we've been working on systems right now that are in the 100 to 500 barrel per day range of distillate. And all of those systems are typically returning water that's somewhere less than 500 TDS at this point. There's some ammonia and some organics carry through that's usually being taken care of in a polishing step to get less than 100. We have a lot of samples right now that are less than 50 TDS water in our database. Some of those also shared with New Mexico. And then ultimately your concentrate then at the end for critical mineral recovery is available, but it's also proving to be pretty challenging in terms of what that looks like. There is a DOE funded project right now at Texas Tech and UT and a group collaborating on critical mineral recovery at this point. So some things that we know, there's a variety of different technologies that are very capable. They're also very energy intensive, some of them on the thermal side especially, in terms of what that takes. And then we also have this waste challenge at the end of the stream and what to do with that. I don't think that there's a very good understanding at the moment based on what our members are telling us about what you do with this concentrated brine in terms of its effect on pore space and injection and things like seismicity. Those are, again, will be important questions as we go forward. So when you start to think about what this means in terms of just energy and water together, I think it's important to paint the picture for the state of Texas in this regard in particular. So if we took the 25 million barrels a day at a 50% recovery rate, we're talking about 250,000 megawatt hours per day. And that's using a 10 kilowatt per hour assumption at this point. Right now, the range, and by all means, our industry partners in this group don't like to share much about the energy consumption or the economics at this point. They're all still trying to work out the details of those things. But we hear a range between 5 and 10 kilowatt hours per barrel. Ultimately, when you think about this particular issue, in the last 12 months, we've heard a lot of companies present at places like Produced Water Society and others that they're running out of pore space. On the low end estimate, some groups would say that they have 18 months of pore space left. On the far end of the spectrum, somewhere around 20 years of pore space left. There's also seismicity issues. We've had a lot of earthquakes in the 5.2 to 5.3 range in and around the disposal well sites that are south of the New Mexico border, also in the Midland Odessa area. We've felt those earthquakes even in Lubbock, pretty substantial ones in recent time. So that's not very good. So there's a serious kind of hazard risk relationship that's brewing here between a limited amount of pore space that's available for some companies, and then seismicity issues caused by injection. So when you think about that in terms of power and again, what that means on that front, ERCOT, the current grid for Texas, has about 150,000, megawatts capacity on a daily basis. Currently, what we've estimated at 10% would be equivalent to 10% of the total ERCOT capacity on a daily basis is what would be required on a daily basis to desalinate produced water at 10 kilowatt hours per barrel. So significant amounts of energy required. On the water front, though, there's some positives about that story. So if we could do it, and we've kind of proven that we can, economics, I think, are the only question at this point. We could generate somewhere around 1,000 acre feet per day, or around 525 million gallons per day. Again, that's about 5 El Pasos per day. When you put that into the context of the Texas Water Plan, similar to what we heard about the 2060 program in Oklahoma, the water data for Texas Portal, looks at reservoirs on the left-hand side and capacities. The water plan actually looks out 50 years in the future, happens on about a 5-year cycle. We're in a rewrite of that water plan right now. Region F is the area that's out around Midland, and this area out here, we're working with them on defining produced water in a more careful way, and the technologies and capacities that should be or could be available into the future. Obviously, there's some connections between certain river basins in the system that have hydroelectric power, and ultimately where the water would be available that you could use in those kinds of systems. Close to the yellow dot on the New Mexico-Texas line there is Red Bluff Reservoir. There's a lot of talk right now about what happens with Red Bluff Reservoir. There are currently 3 discharge permits sitting on the desk at TCEQ, waiting approval for stream discharge. That would be equivalent to 5 times base flow increase, current base flow increase in the Pecos River south of Red Bluff Reservoir on a daily basis. This year, Red Bluff will not be releasing water again because of the low level of water in the reservoir. So that means all downstream producers, ag producers, any other kind of user is struggling to make ends meet on the waterfront. If you look at the 2 reservoirs that are on the Texas Mexico border, Amistad to the north, and then Falcon Reservoir to the south, they're both sitting at about 25% capacity right now. That is a very difficult situation and an international tension between the 2 countries. Another piece of the puzzle for us in Texas is that brackish groundwater is going to have to play a role. Currently, our Ogallala resources, that's the panhandle of Texas, and a lot of the area overlaps with the Permian Basin. We have a significant challenge with water availability in the Ogallala. It's also turning more brackish, and the mineral content and composition is changing pretty radically. That's affecting animal health. We have about 6.5 million cows. This last year, there was a significant population of those animals that were not healthy because of liver and kidney disease caused by water. That's a significant part of this equation as well. So we estimate the Texas Water Development Board has a BRAX program, which is a brackish groundwater study. They've identified about 3.2 billion acre feet of brackish water that could be available for Texas consumption in the future. That's 1,000 to 10,000 MGLs. That's much different than 170,000 TDS water, but it's the same technologies, the same desalination technologies. If we get really smart, really good at it, these are 2 excellent water sources for the future of the state. So in summary, we have a lot of water need in the state. We're short pretty substantially in the next 20 years. Looking out to 50 years, we are really in a pinch in water. So identifying new sources has been a topic of this legislative session. This legislative session, permitting that was typically under the Railroad Commission for land application is moving to the TCEQ. So all permitting for land application or stream discharge will be housed under TCEQ. That's a positive, I think, from everybody's perspective in terms of what happens. There is still tension though between a RCRA waste as it's currently exempted with produced water and in the waste stream, moving then into a Clean Water Act or a Safe Drinking Water Act policy framework. Those don't necessarily talk to each other, nor do surface water, groundwater interactions in the state of Texas, especially in the state water plan. Those are two separate modeling systems and forecasts that are put together, and they're not necessarily identified together. So if you think about the Pecos River system, it's really important to understand what a baseline condition currently is, and then what some positives might be coming out of what we could do with both energy and water. On the industrial front, data centers and solar power are making huge gains in West Texas. Some of the largest solar fields in the United States are right at the southern end of the Midland Basin. There's one county that their county economy has gone from about $4 billion a year off oil and gas production in 2021. Last year, somewhere north of $22 billion, and the increased difference is all solar. Somewhere north of 2.5 million panels at one time. But there's also the energy effect on water that's associated with solar as well. In West Texas, it's dusty. Sometimes you got to clean those things off. That's another consideration as well. Our future work really looks at identifying kind of optimal scenarios on technology and methods. I think that there's a lot on the methods front. The technologies seem like they're shaping up pretty well, but methods would be things like, where do you change pH to then have a better effect on ammonia carry through or not, as one example. A lot of work on now high recovery kind of desal processes, and then, kind of maximizing the water recovery and concentrate disposal equations, looking at all those train cars that we could reduce at some point. That would be great. There's also a lot of work that's now being done, given the fact that we've piloted up some very successful technologies and scenarios in the 100 to 500 barrel range. Companies are coming online with now 5 to 10,000 barrel units in the next 12 months. We're excited about those opportunities and what that means. But that's also going to then pivot over to what does that mean in terms of downhole injection of that concentrated brine? And then how do we handle some of the waste in a little different area? Texas, like lots of places, is highly involved in advanced nuclear alternatives. We've got several projects that are with a group based out of Abilene, Texas, looking at the ways that you could use waste heat off of the reactor in a treatment process and then use water back in a cooling process. So those are things that we're currently working on, and thank you for your time today.
Thank you, Eric. Really appreciate that. Now, Rick McCurdy.
All right, thank you, Nick. And I think I'll do the same thing. I'll just sit here and present, and that way I don't have slides in front of me, so I can kind of glance at the screen while I'm doing it and move forward. So we'll wait till we get my presentation. While we're waiting to get my presentation loaded up, I want to say how happy it is to be speaking to the National Academies again. Done it a couple of different times in the past. Once when they hosted a meeting in DC for the Government Accountability Office to address produced water reuse in operations. And then again, I think it was 2018, the academies hosted a group of us from industry and academia to come in and talk about produced water again in DC. And they came out with a little white paper, a little book that addressed all the different presentations. So happy to be here again. All right, next slide. So this is a standard disclaimer slide that we have to put in here. Now, I could read this and that just burn up my time and then we'd be done. But instead, I'll tell you what my legal department hates for me to say. This slide simply says, Rick is a loose cannon. Select Water Solutions cannot be responsible for anything that comes out of his mouth. Next slide. So there's a lot of challenges and opportunities associated with produced water, and I think you're hearing a lot of it in here today. And this is obviously not a new conversation. We've been having this conversation for many years now, as I mentioned. And as I said, going back to, Secretary mentioned it earlier, I was with Chesapeake Energy for 11 years here in Oklahoma City. And Chesapeake was one of the largest operators in the Barnett. And we had the Barnett Shale Water Management Consortium that was stood up to look at minimizing fresh water use. Back in those days, in the mid
late 2000s, the concept was we could only use fresh water in hydraulic fracturing. And the reason for that is because all the chemistries that have been designed for hydraulic fracturing were designed around fresh water. And so we were trying to figure out ways to do it. And this was even so much to the point, and Paul's aware of this, that as the secretary mentioned earlier, Devon was one of the first ones that they stood up a whole squad of mechanical vapor recompression devices because they could treat the produced water and reuse the distillate in their ongoing completions in the Barnett. So they were one of the first ones to do that. What used outside oil and gas was just returned and used inside of oil and gas. But there's other opportunities to challenge. We've heard mentioned today about seismicity. You're going to hear me talk a lot about the Permian today, and I'll have a slide here in a minute that talks about that. We talk about this shallow zone pressurization, this pore space issue that Eric was referring to. And then there's logistical difficulties. If you think about the volumes of water that we use nowadays and we produce nowadays, the infrastructure we have in place in the ground that's been there historically does not handle those volumes. So we're having to build out new infrastructure consistently, particularly in the Permian, where what used to be 8-inch, 10-inch pipes in the ground are now 22, 24, 36-inch pipes in the ground to move water volume around. And there's a reason for that. When we take a look at our opportunities, we talk about those interconnected water systems to where we can move large volumes. We have one system in the upper end of the Delaware Basin that has 16 million barrels of storage capacity for treated produced water and can literally move it across the large parts of 2 different counties to where if we need water over in this section, all we got to do is pump it over there. Likewise, we can bring water back the same way. And one of this is, we talk about hydraulic fracturing. When the Barnett was originally the first one that stood up these high volume, high horizontal wells with hydraulic fracturing and made it successful. Back in those days, we were talking 80 to 100,000 barrels of water per well. Well, now we're hitting somewhere in the neighborhood of 750,000 barrels or better water per well because the laterals are much longer. We've seen wells that go out in YouTube and come back the other way. And so you're treating all that. And then in addition to that, so on average, we're in the neighborhood of 100 to 110,000 barrels of water per day, per well to complete it. But now we've moved, we had single well hydraulic fracturing. Then we went to zipper fracs where you'd have 2 wells and you just constantly bounce back and forth through the stages between each one to where you were continuously operating. Then we went to simul-fracs where you had 2 crews on location. You were fracking 2 wells at the exact same time. And now the latest iteration of that is trimul-fracs. 3 crews on location, fracking 3 wells at the same time. And we hope that's the goal, that we're supplying 100% produced water for those completions. That's 300,000 barrels of water a day until those wells are fracked. Last summer, we supplied, and my company supplied 300,000 barrels of water a day for 30 consecutive days so that back then it was still Endeavor Energy could frack 12 wells on the same pad and get them knocked out. So that required large pipes, a lot of pumps moving water around. Okay, next slide. Now, a lot of this we've known for a long time. If we can distill produced water, and we've known this for 15 plus years, well, why are we not doing it? Well, obviously it's an economic situation. Not to mention, as we talked about, the using outside oil and gas comes with other concerns other than just economics. We got to know that it's of good enough quality to use. It's not going to do any harm to the environment. I actually used this slide. This was from a presentation in 2019, but I think I originally put it together in 2018. And it was just, and I apologize for the scale on the graphics, but the y-axis is the cost per dollars a barrel on average for these technologies. It goes up to $11. The x-axis is the total dissolved solids content of the brine that could potentially be treated with these technologies. Obviously, from this photo, you can see, or this cartoon, you can see RO tends to be cheaper, but then RO is really limited, at least traditional RO and brackish water RO, to about a maximum TDS of 50,000 milligrams per liter. Above that, we would have vacuum distillation, mechanical vapor recompression, handles much higher TDS, generally very effectively up to about 200, 210,000 milligrams per liter. Cost is higher, as you can see. And then crystallization, taking a produced water completely to salt. And there's a couple areas that's been done, primarily up in the northeastern Marcellus, because of the lack of disposal in that area. Very expensive, creates a ton of waste. Luckily, up in the Northeast, they can find some uses for that much salt. We've talked about doing it here in Oklahoma. We've talked about doing it in the Permian. There's just no way we could find a commercial endeavor for that much salt. We would build the highest point, the highest point in Texas would be a salt mound that we would generate out in West Texas. Next slide. Now, the good news is with time, we are continually seeing the cost of these technologies start to evolve downward. It's through improved efficiencies, it's through some new applications that are being applied, some new techniques, some new membrane technology that's coming along. And with the externalities that we're talking about, such as seismicity, shallow zone pressurization, beginning to see an end in available pore space for disposal, that is driving the cost of conventional disposal up. As those two lines come closer and closer together, this becomes a very real possibility that monies could be applied to recover a beneficial volume of water out of produced water, thus reducing the amount of water you sent to disposal. Next slide. And with that, and this is what I'm talking about, over time, what we've seen is some of the older thermal technologies, we've seen improvements in efficiencies. So with the vacuum distillation, mechanical vapor recovery, we now see that shrunk down somewhat. Really hadn't changed the effectiveness of the water that it works with. Cost has come down. Not a lot of advancement with crystallization, because honestly, there's just not a lot of folks focused on going that route with produced water. But then what's exciting is we are seeing new thermal treatment processes out there. I'll show you a glimpse of one toward the end of this. There's technology such as counterflow RO that uses ultra high pressure RO membranes, where regular RO membranes typically operate at about 60 or 80 bar. These tend to be more in the 100 to 120 bar range, but you can work with much higher TDS waters. There's a company working with freeze thaw technology. So the theory being that takes less energy to get from 100-degree water down to 32 than it does to get up around 212. And then my favorite, membrane distillation. And it's starting to come a long way. And I'll have a slide talking a little bit about it and what we're doing with it at the end. Next slide, please. And the reason I'm mentioning the Permian Basin, if you take a look at this little circle chart that shows all the produced water produced onshore US, the Permian Basin counts for a third of that volume. Plus, currently, that's where we're seeing the biggest impact from a lot of those externalities. Thank goodness the issue that we had in 2011 up through 2018 in Oklahoma with our seismicity, eventually that abated. That abated because the Miss Line play essentially became uneconomic. It was a water moving play in order to get oil out of the ground, the volumes of water that were going to disposal, what were linked to induced seismicity. As the larger operators started migrating out of that play because it looked like cost of disposal and the cost to move water around was going to make it uneconomic, guess what? The seismicity issues went away. Now the Permian, we are seeing it. I will say this, the work that was done in Oklahoma has really led the way for a lot of other states dealing with technology, dealing with seismicity. So when we started seeing it in the Permian Basin, it gave the operators in Texas a framework to work around. Okay, what steps do we need to take to reduce this? And so far it's been effective. We still occasionally are seeing some quakes, particularly up in that, what they refer to as the North Culberson Reeves seismic response area, which up around Mentone, Texas, up by the Texas-New Mexico state line. But they're a lot less in number and they're becoming more and more infrequent as we move forward. Next slide. But produced water isn't slowing down in the Permian Basin. This is a projection now showing out through 2026. By the end of 2026, we expect to have about 8.6 billion barrels of water produced a year in the Permian Basin. Again, a lot of water. Next slide, please. And with that comes an issue that's way more water than we can actually use in ongoing completions. On the left, you see the demand for completion activity in the Permian Basin. And on the right, you see the amount of produced water. So you see a gap there of about 5 million barrels. Now, not all that's going to do regular disposal, get rid of it disposal. Roughly half of that is still being used in those conventional EOR projects. In that Central Basin uplift there in Midland Basin. So those old water floods just keep moving that water back in the ground, back in the ground, back in the ground. So you still have about 2.5, 3 billion barrels a year that's going to conventional disposal for just to get rid of it and store it underground. And we're starting to run out of room there. Now, here's the fear that sits in the back of my mind and sits in the back of a lot of operators' minds that work in the Permian Basin. What happens if we have an event that causes those completions to go away? A couple things could happen. One of them eventually will drill out all the benches in the Permian Basin and you'll have no need for completions anymore. Now, that could vary. That will likely be another 10 to 30 years from now before that happens. More realistically, we could have the price of oil go to $30 a barrel, and then you'll see those completions go away. Everybody will pull them off the table as they try to conserve funds. We don't have the capacity to handle another 3 billion barrels of water and disposal a day if those completions aren't available for reuse. If that happens, then the cost of disposal is going to exponentially accelerate. Next slide. But we have opportunities. We have opportunities for this water, and you're hearing some of it talked about in here today. If we can recover a beneficial, and by beneficial, I'm talking, as Eric mentioned, we're getting a distillate out that's somewhere in the neighborhood of 500, 600 milligrams per liter or less. So it can be beneficially used. We can use it for rangeland restoration. The good news is the vast majority of the areas to where we operate oil and gas wells, there's native rangeland all around it. So it's not like you're going to have to transport it very far to use it. In addition to that, there's work being done looking at non-edible crops, and there's different stages of what we consider acceptance of what we could do with this water. That would be the next step, irrigation of non-edible crops, such as cotton, hemp. Next step up would be irrigation of crops that animals might consume, like alfalfa for cows or horses, or something that we would feed, maybe corn that pigs would use. But then there are other plants as well, such as gauli. That's a unique one. That's a plant, and surprised Eric didn't mention it, but it's a plant that will go good in the kind of climate we have out in West Texas, and it produces a rubber in its root system that can be refined into latex rubber, which is in short supply. And then we're going to have industrial uses, and you're hearing those mentioned here today. Carbon capture, underground sequestration, blue and green hydrogen projects, cooling for natural gas generation to support those CCUS projects. And then data centers. And I know we've got a panel here right after lunch that's going to talk about power generation and data centers. And I'm really looking forward to hearing about that. Next, please. And obviously those activities are going to take a lot of water. When we take a look at blue hydrogen or green methane, where we're taking that hydrogen and converting it back into a synthetic methane, you're looking at hundreds to 500,000 barrels of water a day for those projects, depending on the size of the facilities that's going to do it. Direct air capture of CO2. We're working with an operator partner out in the Permian now on one of those projects. It's going to take a ton of water. Nuclear power is going to need water for cooling, even these small modular reactors that everybody's focused on these days. And then these hyperscale data centers. They're going to demand a tremendous amount of water for cooling and for the power generation that's going to drive the data center. Now, they have the option that they could use a refrigerant-based cooling system rather than water. But to do that, if you have a 1 gigawatt data center and you use chillers instead of just air evaporation to cool it, you've got to build a 1.5 gigawatt power generation facility, because you're going to need a third of the power to go to the chilling. Okay, next slide, please. And critical mineral recovery, rare earth elements that was mentioned here today. That's another possibility and something I think we do need more work on. A lot of people have focused on lithium these last few years, and there's a lot of projects undergoing in different parts of the country now. The Smackover with ExxonMobil's a big project. There's other companies. We're one of them looking at some of these technologies. Iodine, as Shelley mentioned, we extracted iodine here in Oklahoma for years. When I was with Chesapeake Energy, many of our saltwater disposal wells up in the Miss Line had iodine extraction facilities on the front end of them. And it was profitable for that company to extract that iodine. But there's other things in that water we need to look at as well. That how about selectively pulling those elements out and commercializing them? Anything we do to valorize that water takes away from the cost to getting it distilled in the first place, which makes it more attractive. Next slide. And there we go. And so just to give you an idea of what my company, Select Water Solutions, is focused on now. And I do, and I'm a big driver of this within the company. I think that this potential to beneficially recover and use this volume out of some produced water. And this produced water applies in a lot of different areas in the country. We focus on the Permian right now because there's a lot of attention and a lot of water there to work with. But technologies that are going to work there are going to work just as well up in the Bakken, work just as well over in Louisiana. It work well up in the Rockies. So whatever we can do there is going to work to essentially. To that extent, we're investing in the neighborhood of $10 million a year on R&D activities associated with beneficial reuse. We also, I'm very proud to say, have been an active member of all three of the state water consortiums since they've been stood up: New Mexico, Texas, and the Colorado Produced Water Consortium. And another thing is DOE currently works with a group out of the University of North Dakota called the Energy and Environmental Research Center. Our company, under the last several years, has had a contract for a facility right outside of Watford City that's adjacent to one of our SWDs up there. And DOE has used that to run pilot projects through there, looking at different produced water. People can bring their technologies into that facility. They've got complete computer access and communications and all that. Plus they get to get in and out of the weather and work there. So we've been happy to have that facility and have worked with DOE in the past on that. Next slide, please. So just some snapshots here of a desal pilot that we're in the process of running out in the Permian Basin right now for an operator. Not going to really talk, the technology's a little bit innovative, so I'm not at a point where we're ready to talk about that yet, but we thought we would throw the photos out there just to detail. This is a facility designed to recover 400 barrels of distillate a day. So it is, as Eric mentioned, one of the larger scale pilot systems that are in operation now. Unless you've seen a lot of them, you wouldn't know this, but I've seen some of the other pilot cells. This is a much smaller system than some of the other like 500 barrel a day systems we've worked on that were like gigantors, about 80 feet in the air and stuff like that. So much more compact design. Next slide. And so when we look at this pilot process, I said it's a 400 barrel a day system. We've learned through the process that we can only max out at about 370 barrels of distillate a day. Realized that we had some piping and valving on the distillate recovery end of the device that was undersized. So that'll need to be redesigned in the future. We have been able to hit the quality of water that we were wanting to hit coming out of it. As Eric mentioned, one of the things you learn with these particularly thermal processes is there are things that will carry with the distillate. Any kind of VOCs are going to carry through, ammonia carries through. So you have to effectively work on a method on the tail end to strip that stuff out, particularly if you're going to land apply it. And if you're ever going to do surface discharge, you've definitely got to get the ammonia out of it. So we're in the process now. A couple of things. The water that came out of that's going to be used for a irrigation pilot. Our operator partner and us, and we're working with the Texas consortium. We've met with and worked through the Texas Railroad Commission, and at this point in time, they're the ones that are authorizing these small scale irrigation pilots that are on just regular ground, not in a contained area. What they do is you work with them and you apply for what's called a letter of authority, which gives you a 1-year permit to do this. And we've received that letter of authority. So that's scheduled to take place this growing season. And we're also in the process of going through the engineering study to take this technology and move it into a size that'll produce 10,000 barrels of distillate a day. Next slide. And then lastly, my favorite thing is membrane distillation. Been working with membrane distillation for about, on and off, about a decade now. When I was here with Chesapeake, I piloted a couple of units on some of that misline brine, and then kind of had a break there as our industry went through one of its normal downturns, and we kind of quit focusing on looking at technology like that for a while. But the good news is, looking at it again, to the point that I actually purchased a pilot unit off the University of Pittsburgh this last year, and it's a small unit, produces about 34 barrels of distillate a day, but it's allowed us to start playing around with some of these waters. We're at the process now of working with a company, looking at a unit that could produce 1,000 barrels of distillate a day. But if you know anything about membrane technology, you know the Achilles heel for that technology is hydrocarbons and mineral scale formation on the membrane itself. Either one of those get on the membrane, you essentially, sometimes you can clean it, most time you have to chunk it and start over. So that's not a problem. Hydrocarbons is not an issue. I'll put a ultrafiltration device on the front end of it that'll ensure that no hydrocarbons get to it. But this test bed here that this photo is part of our company has a chemistry group. And so we're working with them in their R&D center down in Houston. We set this up. What it is 7 cells that will each hold a 36-inch square piece of this membrane that we use in these. And then we got 7 cells. We're looking at 7 different chemical packages through 7 different various produced waters around the US. And we're going to figure out the best chemical package for each water to prevent that mineral scale formation. Where we see flux rates fall off going through these test beds, we have the ability to pull that filter out, use scanning electron microscope, do forensics on it, determine what kind of scale actually formed on the filter itself. And I think that should be it. Last slide. Yes, thank you very much.
Thanks to the 3 of you for excellent presentations. We really appreciate it. And I'm going to ask a question to kind of kick us off here and ask all of you to respond to it. And I didn't blindside these guys. I reminded one question I was going to ask. They had a little time to think about it. And that is, what is a major issue or problem or group issues and problems at the interface of energy production and water that potentially be addressed through the DOE Regional Energy Water Technology Pilot Project? And in your view, what would an effective project look like? And in that, we're in Mr. Helms Institute, and we're close to being in the shadow of the Devon building. I'd like to kind of emphasize oil and gas, but not necessarily limited to that. So, Shelley, I'll start with you.
Okay, so obviously I am a policy person. That's what I do. So I was kind of thinking about this a little bit from the policy and regulatory perspective. I think one of the first things that we really need to consider is looking at that 98 meridian restriction. It was arbitrary when it was picked. So what does it look like if we take that restriction away? I think we have to look at what are reasonable, appropriate safeguards, whether they be best management practices or actual water quality standards or permit limits, rather than the good enough quality. Because good enough quality has led to an answer of no, that's not good enough. Well, what if we treat to this? No, that's not good enough. So I think that's an area that there could be some focus. Something that Rick mentioned related to non-edible crops or other crops in general. What happens to the soil? What happens to production over time? The Volcani Institute in Israel is doing a lot of really interesting research right now that maybe that can be pulled in to look at production rates and safety rates. In Israel, it's not produced water, but it's other recycled, reused water that has varying levels of elevated salt content. And preliminary results, in case anyone's wondering, over time, the plants do grow smaller and the fruits are not as large as they were on soil not impacted. So I think that's something that we, need to think about. What does that look like? I know in the past there've been some studies on cotton, but what else? I think that's going to drive a lot of where we might go with the disposal concerns, and whether it's partially treated or that fit for purpose treatment, I think is also what we have to focus on. When people start talking about treatment, it's, oh, to drinking water standards, oh, it's to background levels. I was like, I don't need to be able to drink what I'm putting in a data center for cooling water. In case anybody's wondering the usage of some of the new AI technology, a half a liter of water for a simple yes or no AI question. So you can expand that out to how much water we're talking about. I think another area that would be interesting to see what we can do, there's starting to be some bench scale studies on generating power through water movement through pipe. As much water as we're moving here in Oklahoma, we do have a treatment facility that multiple companies use. They send water in, they treat it, send water back out. Well, there is, a burgeoning industry of power generation, that water moving through pipe, not just through dams. So that is a kind of a partnership between oil and gas and other hydropower. But so those would be some things I would throw out that might be interesting to see how we can advance over time.
Thank you. Very good. Eric, we'll go the same order that we did with the talks.
Great, thank you. I think the same things that we talked about in the presentation are probably the most important. So if you think about the technologies that are trying to scale right now, I think pilots that look at, the next scale that folks are talking about is the 5,000 to 10,000 barrel range. That's got a 24-month kind of time horizon on it. 36 to 60 months out, we're talking about 50,000 scale units or systems. The co-location of that with power available and grid reliability in this particular part of the world are really pretty important. So how you start to merge those two things together, I think, are all important topics. We've invested heavily in understanding what the effects would be on both base flow into the Pecos River moving forward by land application and then direct kind of stream application. Mother Nature doesn't rain salt water. So if we treat to rainwater standard, we don't have to worry about what we do with it. It'll fit any of those purposes. Economically, what it looks like right now when you start off with 170,000 TDS water, you're probably going to still have to use a thermal process at the start. How far you desal and where you optimize, then switching to membrane technologies, or what methodologies you use with technologies in tandem for the order of operations on things. There's an awful lot of work to be done, I think, on those fronts in particular. So when you think about downstream effects and power, when I worked at Kansas State for a long period of time, we worked a lot on groundwater-based economies, and we studied a lot of weather patterns and weather movements. And we looked at when Kansas went from being the wheat state to a corn state with an ethanol policy and an enzyme in particular that was lobbied for its use to break down the starches on corn. We started applying a lot of anhydrous ammonia in western Kansas. That fell back out of the sky at the 100th in the tall grass prairie kind of system. And the native species do not like synthetic chemistry. However, so if you took invasive species in the San Antonio, Austin area, and you thought about water consumption in those places, and then you think about power generation through hydroelectric dams, the more invasive species we have there that are taking up water, you're limiting what goes on. So out in West Texas, if we can evaporate more from a land that's regenerated in some way, we can have more water fall back out of the sky at the 100th meridian. If we continue to put a lot of ammonia into the atmosphere in that same kind of process sometimes, we might be supercharging some of those invasive species that are also dewatering the aquifer in the San Antonio, Austin area. So where we start to think about water and energy balances, I think that there's some scales that we haven't yet considered that would be important considerations with like NCAR and others on their kind of atmospheric research and kind of larger scale systems that then downscale to individual kind of hydroelectric power generation and water availability in states. Thank you.
Thank you. Rick?
All right, so first of all, let me just tell Shelley that she'll be happy to know that EPA has stood up a study group
Yes.
that is looking at that 98th meridian language. And it's composed of EPA DC staff as well as Region 6 and Region 8. Put together, and they're going around taking a look at all these pilot projects with the objective being to, let's put some actual numbers in this. If people would probably want to utilize this, if we could give them a goal to get to other than a good enough quality. And so that's good to know. Now, they're not going to do any rulemaking. They're doing this study and then they're going to make recommendations back to EPA about here's what we think should be changed within this. So that's positive there. Second story I'll share real quick. 90th Meridian runs directly through Bee Cave, Texas, just west of Austin. And the Royal Sonesta Hotel there is a 6-story tall hotel. The 6th story is a restaurant and a bar. Name of the bar is the Meridian 98. And I was there for a Texas DSAL conference year before last and happened to be in the bar. And I tell the bartender, you know how the bar got its name? She's like, no. And so I give her the spiel. Here's what it is. It divides. The neat thing about that is I'm talking to somebody and I look up here in a minute, she's talking to another waitress. No, it's just 98th Meridian. Right. Next thing you know, I got a waiter comes up to me. So explain to me this again. How's this 98th Meridian? So that was cool. All right. My wish list. 2 things. One of the things, when we get to where we do this at scale, to where we're able to create this volume of beneficial water, whether it's 10,000 or 50,000 barrels a day, and we're going to do it in an application, whether it's irrigation, or particularly if it's irrigation or if it's going to be surface discharge to waters of the U.S., it's going to require a lot of monitoring to ensure that we're consistently doing that safely. Hey, where we at on the NIPTES plus list now, 400 plus constituents. When you take a water sample into a NELAP approved lab and you say, I need you to run these 400 constituents, get ready to write a check. And we can't afford to write that check if we got to do that every day or every week or anything like that. That'll make this astronomically expensive to do. So ideally what we need is real time monitoring instruments that can give us a value that tells us that that water is within the parameters that we need. We've got the automation to put it in place, got the automation to shut it down, should that give us an indication we've got a problem. But with that instrument doesn't exist, and that would be very beneficial. The second thing I would ask for, and I mentioned this a little bit on the slide on the rare earth minerals, the critical mineral recovery. We know there's some work out there being done. I think while there's value with lithium, there's value with iodine, we have a lot higher concentrations of some of those other minerals in our produced water. And there's some universities that are doing some great stuff with selectively removing some of those minerals. But it's all being done at the lab scale right now. We need a focus on moving that to a larger pilot scale that could go to the field to demonstrate it can be done. And it can be done in a pure form that would make those commercially sellable. Because if we, again, anything we can do to help reduce the cost of distillation makes it more acceptable to everybody in the process.
Very good. Madam Chair, it's your pleasure, but if we could take about 10 minutes of the lunch time and maybe go to the people that are online that might want to ask a question of these 3.
Or the people here who also might.
I was thinking we could do that over lunch as well.
I
Since I hope they stay and have lunch with us.
see, there is some logic there. Go for it.
So I'm not on Zoom, so if you could.
Yeah, if there are any questions online, if you could put your hands up, that would be great. And we'll somehow monitor that. I'm not sure how. And if there aren't, how about questions in the room in the meantime? Yes, Kate.
So I'm really grateful for all the 3 outstanding presentations. And I also learned a lot, even though I serve as a research director of New Mexico Produced Water Research Consortium. So maybe I can give some comments about the produced water research we do in New Mexico. Shelley, to answer your question, you talk about if we apply the treated produced water, how about the impact on the soil, on plants and groundwater? So for New Mexico Produced Water Research Consortium, we developed a comprehensive framework to first to evaluate the treatment technologies of the produced water and also evaluate the risks and the environmental impacts and also the impact on the public health of the using the treated produced water for fit for purpose applications. So Nick and Eric, you both talk about the chemical analysis. So we developed a list called NPDES class list, and it's evaluates over 400 constituents in raw produced water and the treated produced water. And we also have that the non-target analysis to know all the unknown compounds in that the treated produced water and produced water. We also do toxicity, whole effluent toxicity study to look at the treated produced water on aquatic life like fish, bacteria, algae, and water fleas, and as well as the animal toxicity test. Because for the wet test, it's about acute or chronic, but we do long-term, for example, 28 days of toxicity study on fish and also the mice experiments. And so far, the results are very promising. We have not found the toxicity from the treated polished produced water. So we work with Texas Consortium and then to collect the water samples from the pilot demonstration project. And we also do the fit and transport modeling, and then to look at if we apply the treated produced water, what will be the transport of like ammonia, volatile organic compounds that carried over to the treated water on the soil. And then we also work with industrial partners to look at if we use the treated produced water for irrigation, what will be the impact on the plant growth and also on the soil. So all these research are ongoing, and then we have been working with US EPA, the Texas TCQ, and the Railroad Commission, New Mexico Environment Department, because we are created by the New Mexico Environment Department to provide all this science and technology development to support the water policies and develop the water quality standards for beneficial reuse. And here we also talk about the resource recovery from the produced water, and Dr. Huiyao is here as well. So we're also looking at the resource recovery, from the produced water, and eventually if we achieve zero liquid discharge, we just have too much salt. What do we do with the salt, right? So we are also want to convert all these, sodium chloride and the sulfate, calcium, and all the minerals into valuable products so we can offset the treatment cost. And also for produced water treatment and reuse, it requires a lot of energy. And Rick, you talk about membrane distillation. We're also working on membrane distillation, but it's solar energy powered desalination systems so that will reduce the energy consumption for treat of produced water. So I just want to give some comments about the produced water research in New Mexico. Thank you.
I have a quick question for Rick. And thanks to all three of you for your presentations. I learned a lot. You talked about one scenario you were worried about where the market price of oil and gas falls and then reduces demand for produced water because of less need for wet well completion.
Yes.
So that sounds like it's sort of the fast forwarded version of the problem that's sort of playing out over a longer period of time. And I guess I'm curious from a US broad, because since Oklahoma exports so much, right? From a US sort of national interest security perspective, what are the big concerns there? Is it loss of supply, higher prices?
So, sometimes our industry is our own worst enemy, right? We've been so successful with the hydraulic fracturing and all that we put so much of these commodity products on the market ahead of themselves. That's what originally caused natural gas prices to fall tremendously back during the 2011 timeframe.
Yeah.
Right? And they're just now kind of slowly recovering. They've kind of gotten back up and they've ebbed and flowed. And hopefully the forecast is, particularly as they bring more and more of these LNG export things online, where we're moving this overseas, moving it to Europe, that it's going to kind of help support pricing. within the US, it is the oil production. And a lot of that, even though now we're the world's largest oil producer, we're still at the realm of OPEC and the OPEC plus countries. You know, they've kind of held their production back now for a couple of years, but then have recently indicated that they're going to start bringing those cutbacks back online in sections. If we get ahead of world consumption, then the commodity prices start falling down and falling away. The President Trump and his drill baby drill philosophy is a great concept. I mean, I understand where he's going there with us being dominant with American energy, but at the same standpoint, the industry really likes having oil about $70 a barrel to maintain constant returns and constant activity. We saw it drop down in the low 60s and high 50s, and that started giving everybody a little pause and a little concern. And the question was, where was it going to go and where is it going to go? Because it's just kind of stabilized. It hadn't really kind of floats right along in that area right now. You get much outside. There's several areas to where most wells still provide a positive rate of return at that price for an oil well. But you get much below that, and a lot of those areas start falling off. The Permian's been identified as one of the places that could likely survive going down to about 35 and still having a lot of benches that would provide a positive rate of return, meaning that that particular well is going to produce enough oil over its life, even at that price, it's going to pay for itself plus a rate of return. But if even at that level, there are some benches, some formations where that is going to be, it's going to be a lot of them out there. It's not. Keep in mind, the way operators work is they identify this land that they've got leased, and they identify what they call as their tier 1 property or tier 1 acreage, tier 2 acreage, tier 3 acreage. Tier 1 is what's going to be optimally the most productive out of the land that they have. That gets completed first. Then they go to tier 2, then they go. Most operators now are on tier 2 wells, which means they are not as profitable as the tier 1, but they still are profitable. Eventually they'll move to tier 3 if they have that much acreage to deal at. And that'll be even more susceptible to these lowering commodity pricing.
I guess my question was, is a lack of demand for produced water or an ability to just inject it underground something that could limit supply from the Permian? Like,
Absolutely.
okay.
Yeah.
Okay, absolutely. So that's where, I think I've used the example before that particularly when we're talking like $80 a barrel of oil.
Yeah.
Well, if I've got a well that makes, in the Midland Basin, let's see, it makes, let's be real easy, 100 barrels of oil a day and 400 barrels of water. Because it's typically a 1-to-4 ratio there. Well, at 100 barrels of oil a day, that well's making $8,000. If I shut that well in because I got nowhere to go with that 400 barrels, now all of a sudden that water, the value of that water is $20 a barrel, because that's what it just cost me for that well to be shut in. So if I lose that option for disposal and I have nowhere else to go with that water, it gets real expensive real fast.
You can ask one more quick question. It sounds like the gas from the Permian is not necessarily the marginal market price setter nationally, right?
Yeah.
But it does have very specific sort of acute water management problems. Is relative to the rest of the US, is the rest of the US also heading towards this cliff of what to do with produced water?
So it depends. And to some degree, yes, like the Haynesville, for example. Most of the geology in Louisiana is not really conducive to disposal. There's a few disposal wells over there, but for some reason, when you go across the Sabine River into East Texas, then that geology is. And I should have explained earlier when I had the one slide up, had all the little red dots around various parts of the US. Those are class 2 saltwater disposal wells that we operate. And if you could see there in East Texas, there was this big agglomeration of them. And that's because we have a pipeline bored underneath the Sabine River that comes up in East Texas. We take about 100,000 barrels of Haynesville shale water out of Louisiana a day, pump it underneath that pipeline into East Texas, and then it gets dispersed out to these saltwater disposal wells over there. But there is a limit. Sooner or later, there is a finite limit to how much water you can put in this ground. That eventually you're going to fill it up. Now, there's some estimates, well, we still got 30 years to go. We're fine. Others, not so much. I think 18 months was mentioned earlier. I know I just met with an operator last week for lunch. He said, where I'm operating at in the Permian, my geologists tell me go got 36 months. And then our disposal capacity in our wells is gone. So we need to be looking at options.
Thank you.
You want?
What some of the responses to that have been are pipelines out of basin, to find additional kind of pore space to inject in outside of basin. Some of those pipelines are pretty expensive, in the billions, range. So you're getting closer and closer to that point where you're gonna start shutting in production. And then you're affecting 8% of US GDP.
Right.
In Texas, are there any restrictions on interbasin transfers and would produced water be considered water for an interbasin transfer?
Rick can correct me if I'm wrong, but the only thing that right now has an impact is SRAs, so seismic reduction areas. So long as you're not impacting another SRA, there isn't really a restriction at this point.
So,
Sorry,
oh, I'm sorry, go ahead.
I was just gonna say Sophie had a question, but go ahead.
Oh, I just wanted to add to that. Within Texas, there are no restrictions on interbase transfer right now. It's just who's willing to pay for the pipeline to move it. So a lot of these, what we're referring to now is these long haul pipelines that are on the books and being designed. They're gonna typically take water out of like the Delaware Basin, the upper Delaware Basin where these seismic areas are, and they're gonna move it 80 miles. So if we go back over into that Central Basin uplift, the Central Basin uplift is where all of these old conventional fields are at. The stuff that was drilled out during the 1920s and 30s and 40s and 50s, and where there's a lot of this real porous rock where they've had these water floods and stuff in place for years. And they're moving that water over to there because a lot of those water floods are essentially depleted now. They've kind of produced them out the best they can. They're going to move water over there and dispose of it in some of those formations, and that's going to be allowed. Keep in mind, that's going to add somewhere in the neighborhood of $1 to $1.50 a barrel to the cost of disposal just to move that water from one place over to the other. Now, there is a separate topic. This was considered last year in Texas. They elected not to act on it because of the seismic areas and because of pore space. The question, there's 2 million barrels of water a day that comes out of New Mexico into Texas for disposal. So the question was, and into an area that's had this seismic activity. So there were two questions. Number one was, should we stop that to help with the seismicity? And they're essentially using pore space that belongs to the citizens of Texas, the landowners in Texas. Because incidentally, the Supreme Court in Texas just ruled recently that the pore space below your land belongs to the landowner, not the mineral operator. So that was what I was going to add on that. So the concept was they kind of took a look at that. They decided there's only two ways that could happen. It would have to be by executive order from the governor saying we're going to stop that, or legislation would have to be passed and say we're not going to allow that interstate movement of water. But the other problem was there, I just mentioned water in Louisiana that comes into East Texas. Okay, how do you do this without doing something with that? So they elected not to do anything with that.
Works for ERCOT.
Yeah.
Okay, one very quick last question, then we get to eat.
Yeah, well, realizing I'm probably gonna be between the lunch. So just a quick question. I think so far the discussion is gonna focus on how to put the produced water to use. And I understand the economics and where this is headed. But what about cutting the produced water down? So in other words, reducing the water use in the first place. And where do you see the industry headed in the next 5 to 10 years? In other words, can we lower the 1-to-4 ratio that you mentioned to 1-to-8 or 1-to-16?
So, there's been work done on that in the past. There's been in some of these conventional wells, particularly vertical wells, to where we can isolate more wetter areas of a thickness, of formation thickness. There have been products, selective permeability modifiers, right? Or just water block off agents that we could say, this section here, this 20-foot section, we're gonna give up the oil that's there because we just don't want the water. So we're gonna block that section off and just produce above it or below. There's also relative permeability modifiers that companies have worked with in the past. Put this out into a formation, and literally it's a polymer that when oil touches it, it retracts. When water touches it, it extends. And there's been some success, but those tend to be only in like really porous sandstone, those products worked. These unconventional reservoirs, forget it. We're not gonna get those polymers out into the formation like that. And I don't think it's gonna work in these horizontal wells. So, but it's not, no reason we shouldn't continue to look at it.
Great. Well, I think on that note, that we should look at filling our pore spaces. So anybody who has more questions, please nab these people while they're eating. And those online, if you have questions, you can send them in, but in the chat, I guess, we'll leave it on. But thanks everyone for your great comments and presentations, and we'll go have some lunch and.
So you want to give a round of applause for Shelley?
Yeah.
Interesting things. One of the more interesting things I got to do during my career was to be one of the investigators for the August 14th, 2003 blackout, which affected about 50 million people. And that's the picture there is from the blackout that occurred in New York City, and that's people streaming out of the city. So we obviously go to a lot of lengths to keep the lights on and have good reliability and resiliency. You can go to the next one. Okay, so this is a quick coverage of the electric grid. And in the electric grid, we really only have three main parts. We've got the generation, and the generation creates the electricity. It used to be that coal was king up to about 2008. I think it was more than 50% of our generation capacity is coal. That's fallen off. Now it's natural gas with wind and solar rapidly developing. The second part is the loads, and the loads consume the electricity. Traditionally, the customers have been in essentially complete control of how much electricity they use. So the goal of the utility was to provide the electricity from the generators to the load. And the way they did that is they use, and they still do, use the transmission distribution system. We use the word transmission to think about the high voltage wires, usually electricity that flows at over 100,000 volts, or what we call 100 kV would be part of the transmission system. And then the lower voltage is the distribution system. Typical voltages in the US go up to 765 kV with 500 kV popular, 345 kV, 230 kV, 161 kV. Some of the reason for these weird numbers, like you might think, why is it 345 kV? That seems like a strange number. Is these are line-to-line voltages. The high voltage grid is three-phase, and we talk about the voltage between the wires and the voltage to neutral. The voltage between the wires is square root of 3 greater than the line to neutral voltage. So if you take some of these weird numbers and divide them by square root of 3, you get more even numbers. Okay, you can go to the next one. The grids worldwide are interconnected. They operate at either 60 hertz or 50 hertz. 60 hertz is common here in North America, 50 hertz in most of the rest of the world. The idea is that when you have a bunch of electric machines connected together, we call that a synchronous grid. So all the generators are turning in sync together at a specified speed that depends upon the frequency. If two grids are operating at the same frequency, like we have here in the US, in the lower 48, we've got the Eastern interconnect, we've got the Western interconnect, and we've got the ERCOT, and they're shown on the different colors there. They're each 60 hertz, but we can't transfer power between them unless we take it from AC, convert it to DC, then convert it back into AC. So there are grids worldwide. I did update this map because the one that I was showing before had Ukraine as part of connected with Russia, and I can tell you Ukraine is not interconnected with Russia. We actually did a study where we looked at interconnecting the Eastern grid and the Western grid together, and it turns out that it's fairly straightforward to do. So we could make a single grid in North America and in the most in North America It's just right now, there's more political reasons rather than technical reasons for not connecting them together. Texas could be easily interconnected with the east, but it's separate because of more of a political issue, not a technical issue. Okay, you can go to the next one. If you are interested in seeing maps of the grid, they are actually available online. That website there shows essentially all the electric lines worldwide. Prior to September 11th, a lot of the maps were available and you could download them. And then after September 11th, maps of the high voltage grid became harder to get. And there's kind of been a debate in the industry saying what is what we call critical energy electricity infrastructure information, or CEII. What should we be sharing publicly and what shouldn't we? And for the most part, the grids are available, and this gives you an example. What's not available are the engineering models that we need to make sense of them. On maps like this, and I included the whole of the US and then a zoomed in view on Oklahoma City, the different voltage or the different colors represent different voltage levels. In different portions of the country, different voltage levels are common. Like in TVA, they use a 500 kV, 161 kV grid. In Texas, we use a 345, 138, 69 kV grid. And that's also common here in Oklahoma as well. The reason for the higher voltages is because when you up the voltage, the amount of power you transfer is equal to the voltage times the current. So if you want to have lower current, you up the voltage. The reason why we want lower current is because the losses in the wire depend upon the resistance of the wire times the square of the current. So you can transfer power actually very long distances on the high voltage grid. People will always ask them, they'll say, how much electricity is lost in going from the generators to the load? The typical value is on the order of 10 to 15%. Maybe 3 to 5% is lost in transmitting in the transmission system. 10% might be lost in the distribution system, which are the more neighborhood wires. So we can move power long distances. You can go to the next one. This is a source of generation. You know, if you want to see how it changed historically, I mentioned that coal was king up to about 2008, 2009, then it's fallen off. The issue with coal is to make electricity with coal, you have to produce twice the amount of carbon dioxide as with making it with natural gas. Natural gas has replaced coal, nuclear stayed pretty constant. Hydro stayed pretty constant. What's been growing is wind and solar. Okay, so you can go to the next one. This just shows the variation in the generation. The thing about the generation in the US is what predominates in different regions is very specific to that region. For example, I work a lot with the utilities in the Pacific Northwest, and they have a lot of hydro resources there. Worked a lot with TVA. TVA has a lot of hydro. You work in Texas, in Texas, we don't have hydro. Okay. What we have in Texas is a lot of natural gas, and now we've got a lot of wind and we've got a lot of solar. And this part of the country has a lot of wind because it's windy here. As I drove up from College Station, I started to see the wind turbines. We don't have wind turbines around College Station because it's not that windy, but once you get up to North Texas or into Oklahoma, then you start seeing them. Nuclear scattered about, coals in certain regions. So it's very region specific to some extent. It's like some people want to have a lot of solar. And I live in Texas, and Texas is pretty sunny, but I grew up in Wisconsin, lived in Illinois. And if you know Wisconsin, Illinois, they can have very gloomy days in the winter. So it's like if that part of the country wants to depend on solar, they've got some major challenges in doing that. So you can go to the next one. So this is where I talk about the transmission distribution. I mentioned the fact that power is equal to voltage times current, I talked about the different voltage levels, I talked about the grid being three-phase. The reason why it's three-phase is because with three-phase, we can move twice the amount of power for the same amount of wire. So pretty much everything is three-phase, and I talked about the losses. When I talk to, pretty smart technical people, a lot of people think we lose a lot of electricity. We don't, okay, it's very low. I mean, the transmission losses are about 3 to 5%. And as I said, it's the distribution is higher because you're using smaller wires at lower voltages. You can go to the next one. Okay, so one of the challenges we have with the grid is that we don't have good ways to store electricity. This is gradually changing, but for the most part, we have to continually match the generation to the load. And with the customers being in command of the load varies continuously, so the utilities are constantly changing the generation to match the load. So that is one of the challenges. Another challenge is we don't directly control the flow of power on the high voltage transmission grid. We indirectly control it by where it's generated, but there's no real valves that you can open and close. Y'all are from the water side, so you use the valves. We don't have those valves. So it's like we put it in and it just kind of flows. The main takeaway on an electric grid is ultimately it is an electrical circuit. So we are operating these big electrical circuits and things move fast in electrical circuits. So that is a challenge. Customers have been in control. And the grid has limits, and sometimes it's thermal limits on the transmission line, sometimes it's other types of limits. And a lot of times we operate the grid close to its limit for economic reasons. How much electricity costs to generate in one region versus another changes with load and lots of things like whether the wind's blowing and stuff. So you want to be moving a lot of power around. So we try to move a lot of power around. So we push the grid to its limits very, very often. We go to the next one. The electric grid operates on different timescales, and when I talk to people in the water domain in Ashland, and I worked a lot when I was at Illinois on water couplings, the water couples with the electric grid at certain timescales. In a lot of the timescales, which are very fast, the dynamics of the water are much slower than that, so there's not really that coupling. But there are certainly a lot of couplings, and I've got that on the next slide, and then the other two speakers are going to build on this. But we do, when we analyze the grid, we have to talk about these different timescales. One of the big changes, and we've talked about this, and we're going to talk about it more, is the growth in electricity. I got started in the electric power industry in let's say the 80s, and at that time, the electric load had been growing rapidly, but it was falling off. We then went through a period over the last maybe 20 years where electricity usage has grown very slowly. But now it is starting to grow again. And in some places like ERCOT, we are talking about potentially doubling our load in not too many years. I don't know if it'll actually double, but it's certainly growing much more rapidly, and that's going to affect a lot of things, including water usage. So last slide, I think, for me. I did want to at least say the word water here a little bit because the other speakers are going to build on that. And it's like I can only cover so much in the time that I have. But there are a lot of couplings with water. Certainly one of them is cooling. And you mentioned, Shelley, about how much water it takes in a data center to do a web search. There's a lot of water usage with cooling, and that depends on the technology you use. Right now, actually, a lot of storage is done with water, pump storage, hydro, and we have right now in the US about the same amount of storage capacity in gigawatts by using water than we do using batteries. Now, batteries are growing much more faster, of course, but I was kind of surprised when I saw that, how much we have. It's about 23 gigawatts. To put that in perspective, though, the total US generation is on the order of maybe 1,200 gigawatts. So we have very little storage capacity right now. But a lot of it is water. Of course, water is a fuel source, which is hydro. And then we're going to hear a lot more about the use of water in the load. It's used for cooling, as has been mentioned. And then people have also mentioned that water, we pump water. That is a load. We use water treatment plants are a load. And then we're going to pass it on to Brandon next. Okay, so look forward to this discussion.
All right. I assume everyone can hear me okay?
You might need to turn it down a tiny bit, but yes.
Okay. And I should share my presentation, right?
Please go ahead.
Yeah. Okay. All right. Well, Tom, thank you for the setup. I think that was excellent overview. And I think it's going to look like we coordinated so well.
Well, we did.
Yes, of course we did. So definitely I want to cover, just a little bit about the energy supply or the electricity industry evolution. As Tom kind of covered, there is a lot of things changing in our industry. And our industry as a whole, and I'll just put up this slide, kind of shows a similar view of what Tom showed. But the bigger chart is really the energy piece, so where the actual electrons are coming from. And then the smaller chart is actually the capacity. So it gives you kind of a different fuel mix, fuel blend of what's going on. And this goes all the way back to 1950. And so you can certainly see, how long coal was king, and really where that drop off was, with the shale gas revolution in the 2011, 2012 time period where gas started taking over coal. So this picture we like to show to say, like, our industry has always been continually evolving. But there's a lot of, a confluence of a number of events that have really gotten us to where we are today. And when we look going forward, we have a significant challenge. And, one of the things that I'm looking forward to some of the questions and discussions on here is that, one of the things I gathered from the previous presentations is this is a very technical group of folks that are really into their different areas of expertise and love to dive deep into it. I am as well. I've been in the power industry 27 years, started working at a coal plant, and I love to get into the details. But the challenge of today is a lot of big picture thinking. One of the things that I like to say, or at least I heard recently in a kind of an overall energy supply leadership forum, a lady who represents the nuclear industry stood up and said, I'm looking at a room full of industry experts, and none of you believe you have the answer to this problem. And everyone's kind of looking around, shaking their heads. And she goes, that doesn't scare me that much. What really scares me is everyone outside of our industry thinks they have the answer. And that's really what our challenge is explaining the challenges that our industry has, connecting with industries like the oil and gas industry, like the water industry, to try to solve some of these complex problems. So really, what are those problems? So obviously, in the US, we've been focused on decarbonization. There's also been, a focus on like climate resilience and climate change in general. And so obviously you see the wind and solar picking up as far as their contribution to the overall industry. And so, and then, you know, with that, you've got coal coming down, you got gas coming up, and you basically have nuclear being flat. And so one of the dynamics I would like to introduce here that Tom kind of touched on, but I want to dive into a little bit is what happens as the capacity of wind and solar start to increase and coal capacity start to decrease. Coal is a dispatchable asset. So again, you have a lever to pull. I need this amount. I can dial my lever in to be that amount. But wind and solar are more variable. So the sun's out, you get this much. The wind is blowing, you get this much. And then all of your dispatchable generation has to back off and react to that. The other dynamic that comes from wind and solar is their inverter-based resources. So versus having this spinning mass in the form of a generator at a gas plant or at a nuclear plant, you now have these inverter-based resources. So the grid itself is now more challenging to operate because you have these variable assets moving up and down. You've got dispatchable that's trying to fill the gaps. You've got energy storage trying to be a player. And then you've got these inverter-based resources versus these more mass inertia-based resources. All of those are creating challenges. And these are problems that we're seeing today. Again, as those inverter-based variable generation is peaking up, what are we starting to see? We're starting to see reliability concerns. So again, here I've a lot of information on this chart, but you know, on the left-hand side, we kind of have these different load shedding events that have happened over the last few years. All of this information comes from NERC. Also, you've got 24 and 24 and 25 winter and 24 summer. I think NERC is putting out their 25 summer, or already has their 25 summer information. You know, how do you look at this chart? You want it to be completely gray. You don't want to see any orange. And so we're seeing events in the United States almost somewhat daily, depending on the seasons. We're concerned as we go into the winter, as we go into the summer. And so we're starting to see these problems. And so, you know, again, one of the things that, you know, certainly weather instances, people tend to point towards climate change. And certainly we're seeing more frequent severe weather. But in some instances, those severe weather instances aren't necessarily as bad as there were in the past. But because we have more wind and solar, more variable generation, more inverter-based generation, we're starting to see more problems. And not a US example, but I will tell you, if you stay up on our industry and read the news and what happened in Spain and Portugal a few weeks ago, what has Spain and Portugal been doing? They've been rolling off their dispatchable generation, in a lot of cases nuclear, and putting on a lot more solar generation. So again, was that the only factor? No. Was it a major factor? Yes. So we have an evolving grid. We're decarbonizing, which is good, but we're starting to get and experience much more reliability challenges. And as Tom said, this is all related to our fuel, our energy supply mix today to meet the load of today. But what is happening? We're starting to see load growth. Similar to Tom, you know, my first, I think 15 years in the industry, I worked in an area that saw like zero load growth. In fact, I think we celebrated when we saw 0.1% load growth that was projected in our areas. We're starting to see areas, like Tom said, that are planning to double their capacity like in the next 7 to 10 years. And what is driving that? Certainly data centers, AI, that gets all the publicity, and you can see that here in the blue. But a lot of it is just general electrification. Electric vehicles, electrification of industry, you know, people buying, getting rid of their gas stoves, getting rid of their gas furnaces, going to electric heat pumps. All of that electrification of the economy drives load growth. Data centers in the short term drives what you're seeing now with that, you know, hey, I need to double my capacity in the next 7 or 8 years. That's a lot coming from the data centers. But if you look at it in terms of the next 20 years, it's electrification that drives that. And so what you see here is just, this is our net zero decarbonization modeling. I would plug that. It's free to the public, so you can find that on our website. And this gives you kind of the range of what, you know, what resources and what drives the load. And we have a wide variety of different scenarios. I think there's like 17 different scenarios. Obviously, future is uncertain. But you can see, depending on what scenario you pick, the drive for electricity goes up and goes down. And if you look at those little pink bars, those pink bars are electrolysis. And so when you think about decarbonization, hydrogen was all the rage a few years ago. People still are talking about building a hydrogen economy. And what does hydrogen take a lot of? It takes a lot of electricity, and it also takes a lot of water. And so kind of going forward, and this is kind of a chart that we show in looking at these different decarbonization options. And I think, again, this is not our quote, but you know, low carbon doesn't exactly mean less water. And in a lot of cases, some of these low carbon electricity resources take a lot of water. So again, hydrogen production, again, all the rage a few years back. A lot of our work was showing that in a lot of cases, the water usage for those was actually being understated quite a bit. Not using the general stoichiometry of creating hydrogen from water, it was more of what about the cooling? And so a lot of cases, the cooling water was left out of that. And then if you go into different carbon capture technologies, so if you're going to take a gas plant and do a 90% carbon capture system, in a lot of cases, that's going to double the water consumption of the plant. So again, same electricity capacity output, double the water consumption. So again, what happens, and this kind of ties into our discussion here today, what happens if you think about just decarbonizing the electricity industry without considering water whatsoever? And we actually have an answer for that. And so we've dove into the same net zero decarbonization modeling that we've done. And again, it's our regen modeling. It's actually been in the news because it's actually out there free to use if you'd like to take a test drive of it. If, you know, economic modeling is your hobby, you can try that. But we kind of break it down by different regions. So this gives you the different regions of the US. And what we basically did is we have the ability to tie water consumption into the model. So it's an economic model. So basically, if one thing is cheaper than the other, then it builds that versus the other. And so if we turn off the water consumption piece, say, don't concern yourself with water. So what if we all ignored our great discussion that we're going to have today and say, the electricity industry can just do whatever they want. They don't have to think about water. Well, this is what that shows you. So again, you can see these are consumption numbers. So we're looking at 4 times the consumption in the Southwest. I think we could all agree that that's probably not doable. Great Plains, 5x, Upper Midwest, 6x. And then where I'm at today here in the Carolinas, Virginia region, 4 times the consumption. I think there are some that stay relatively flat, but in general, you see areas that are already water starved would see their consumption just kind of go through the roof relative to the electricity industry. So to kind of bring it home, this is my last slide, what I would say is that, you know, what do you tell folks when they say they think they have the answer when it comes to decarbonization, it comes to energy modernization? We'll have to say always, well, if you're not factoring in the water, you're probably making a giant mistake. So again, I appreciate everyone's time. Look forward to your questions.
All right, I will go up to the front as well.
This definitely will look like we coordinated really closely and really well. Yeah, right? That's right. No, I think this is good. I think, what we heard from Tom and Brandon is much more about power systems overall. I'll be diving into a lot more on the water related aspects of this and what are some of the water related implications on this. So you can go to the next slide. So this map here shows more or less sort of present day water withdrawals on the left and water consumption on the right of the US power sector. And so you can see there's the darker pinker or the pinker colors sort of where we see more water. We're seeing that not only around here, Texas, but then going up sort of that 98th meridian maybe. And then further east, where we definitely see a lot more withdrawals, as well as a lot more consumption of this. Where you see those, those colors are where we have power plants. And if you go to the next slide, as Tom noted, in different places, we have different types of generators. So Tom showed you a map that highlighted the different types of generators we have in different locations. Well, each of those generators will have a different water requirement, both different amount of water withdrawal that it requires or a different amount of water consumption that it requires. This is going to be based on the fuel type that you're using. It's also going to be based on the prime mover type or the generator type, whether it's a steam turbine or a combined cycle type unit. And then also it's going to be very heavily dependent also on the type of cooling system you have. If it's a once through system, it's going to withdraw a lot of water, consume very little. If it's a recirculating or a cooling tower system, it's going to withdraw relatively less, but consume a higher percentage of that amount that it withdraws. You also know, we should go to the next slide. We also, do look at water at a life cycle basis, but really most of the water that is used is going to be withdrawn and consumed at the power plant level. And so much more, water is going to be used for natural gas. We talked about those large volumes of water for gas development. That's dwarfed. It's orders of magnitude more water that's used in the power plant than in that actual drilling and completion activities. There's also water required for manufacturing, but really the lion's share is going to be in operations. Big exceptions, I think, to that are well, Eric, I think you had mentioned, you can use water for solar panels to clean them off. That's fine. That's still, going to be, about a third of the amount of water that's required for manufacturing those PV panels. So that's a case where the actual manufacturing the PV panels can require more water. But it's still going to be an order of magnitude or multiple orders of magnitude less than you had a natural gas or a coal or a nuclear plant there for that operational water usage. So all we just want to highlight is that all these different technologies have different water use rates. And I think that's it's really important given the region where you are, which may or may not have different levels of water availability. If you go to the next slide, we can highlight this dependency on water does and can lead to power sector vulnerabilities, or at least individual power plant challenges, where you might have to shut down or curtail generation from a generator because either you do not have enough water, or because the water is too warm on the intake, or the water might be too warm as you're discharging it, and so due to regulations, you're not allowed to discharge. So here's, I think this is even a little bit dated now, but it still highlights all across the country. We are seeing places where specific power plants have had to shut down or curtail generation due to that water. That's historical. If we go to the next slide, this map shows some work we did looking forward. So thinking about if we keep that even just that same fleet of generators, but then we look at further implications from temperatures or changes in water availability and water temperatures. We were seeing some power plants that might have up to 10 or 15% of their total capacity that would be reduced as a result of these changes in water temperature and or water availability. On the national level, it's only about 2.5% by 2050. But again, we are seeing very regional differences in where we could see potential more extreme impacts on our available capacity for these individual generators. So that is, you know, that one thing you might say is, okay, great. This helps us identify, you know, where there might be some problem spots. Let's think about water stress and water scarcity, and let's not cite things in those areas. We go to the next slide. One of the big challenges that we face is, you know, there's 50 nifty United States, and there's more than double that number of different types of water stress and water scarcity metrics that are used. And so, and each of those, you know, has a different, you know, set of boundary conditions, as well as oftentimes different thresholds for when you might say a place is water stressed or it's water scarce. There's, you know, at its core, we think about water stress or water scarcity being, you know, how much as a fraction of how much water are you using divided by how much water is available. And again, we're seeing different boundary conditions on those categories, especially as it relates to water availability. So when you think about water availability, you've got physical water that's available. You've also got legal water availability, whether it's related to water rights in the West or environmental flows or other different sorts of restrictions or constraints on what you can do with that water. So if we go to the next slide, I did want to highlight some of the work by Vince Tidwell from his time at Sandia, really doing a deep dive into how do we characterize how much water is actually available for the power sector. And this is, you know, very detailed work. And yet, you know, it really is somewhat limited. It's almost not at a high enough spatial resolution for investment decisions to be made. It's also really not at the right temporal resolution. It's sort of, these are static maps as opposed to thinking about seasonal water availability, as well as changes each year as we see transitions from, you know, water out of agricultural, primarily agricultural water rights moving towards residential or other types of systems. But even with this, this I think, you know, is some of the greatest data that we have. I still think it's highly limited in terms of providing us the right level and the right types of insights we need to make these you know, improved investment decisions. So if you go to the next slide, I'll just do a little bit of example. We heard from a little bit about the use of brackish groundwater, beneficial use of brackish groundwater in Texas. This sort of builds up, you know, one of the areas where we have the most amount of data is on brackish groundwater in terms of alternative water resources. So we've done a study here looking at how can we use brackish water in the power sector? Can we use brackish water as a replacement for fresh water for cooling or other purposes in the power sector? So that this map just highlights where we've got certain levels of data of brackish water resource. And if you go to the next slide, we can also then compare the total amount of water that's available, brackish water, compared to how much water we're currently using for thermoelectric cooling on the power sector. So it's hard to see a little bit, I think, for everybody, but there's a handful of states have hashed patterns on them. Those indicate we actually have more brackish water available at a very conservative yield rate than we actually currently use for thermoelectric cooling. So those are theoretically states where we could meet all of our power electric demand with brackish water. But if you go to the next slide, all these things most certainly come at a cost. And this is, you can't see this at all, but this highlights state by state, basically how much brackish water they have in these black triangles, and then how much water they need for cooling in the green squares. And then all these values down here highlight the costs of doing that. So we can do anything we want, but it's all going to come at a cost. And here comes the real decision point of, is this valuable? Is this worthwhile to do? But we've developed this nice framework where we're able to sort of pool together all the different sources of water, as well as then map them to all the different end uses of water, and think about creative ways to figure out transport and figure out where to develop and where to build certain types of water treatment systems for the most economic use within these various end uses. This is just an example for the power sector, which again shows you, it's possible, we can do it. But the big question is going to be, would it be worth the price? And in many cases, the likely answer is probably not, compared with what people are currently paying or not for water. But at least here we have an ability to look at the cost. This same framework we're also using right now for looking at other types of sources of alternative water, whether it's municipal wastewater, agricultural runoff. We have looked at produced water as well, and then for other sorts of end uses, whether it be drinking water or if we go to the next slide, things like data centers or other things that I think Brandon did a good job highlighting. Hydrogen, you know, if we're looking at that, where are we going to be developing these hydrogen systems? This is a map showing data centers. Where are we going to build the next data centers? What are all the constraints that are going to go into that? Only one of which is water, and frankly, water is oftentimes a pretty minor cost element to this, at least now. But we can look at what are some alternative water sources and other opportunities that are there that we could use for doing this. But I think Brandon, really highlighted some of the emerging trends. You know, the way the energy sector has developed over the past even decade is likely to be different from what has happened, what we will see going forward. New sources of water demands and new sources of power demands could drastically change that the overall map of what our energy sector looks like. And if you go to the last slide, I'll just highlight some other work that we're doing in conjunction with EPRI, and Nellie Rao is really the person you should talk to about this. It's a climate and water risk assessment tool. So this is really laser focused on thinking about our power sector and our generators and where they may face different types of risks as it relates to changes in temperature related to climate, or these changes in water temperature and water availability that I spoke about earlier. So that's a resource that's freely available. It's been a great effort working with EPRI jointly on this. So that's my last slide. So thank you very much, and I look forward to any questions you have.
Big thanks to our speakers. I think we've got about half an hour. Are we sticking to our normal schedule? Excellent. So get your questions ready. I'm going to take moderator privilege and go first. But we will, I think, maybe start in the room and then go online, given that we have a decent amount of time. My question for our speakers, I think, mostly touches on something that all of you brought up, which is basically that we're resource constrained in a lot of these situations, and also that there are a lot of different reasons why we might expect electricity demand to go up. It does seem from the news, people are being a lot more reactive to the potential demand increase from something like a data center. But when you think about allocating water and power and money for power that's maybe going to people's heating versus a data center or something like that, and what we consider to be worth it, especially in the context maybe of pilots or demonstrations, I'm wondering if the speakers could maybe talk about how you might think about prioritization there.
Prioritizing what?
People versus.
Or like who gets it? When are you willing to spend the extra money? When are you willing to spend the extra water? These kinds of things.
Data centers versus people.
I mean, I think it's very telling over the past few decades how rapidly the United States population has increased, and yet other than very recently, most of our electricity demand has stayed on a national level has stayed relatively flat. And I think that's really a testament towards advancements in things like energy efficiency and improved technologies on that front. We haven't seen as much. There's a lot of doom and gloom, I would say, about data centers in terms of dramatically increasing our electricity demand, dramatically increasing our water demand. I think there's opportunities there for efficiencies and for thinking about ways in which we can do this better. And I think that to me is a key area for not only learning by doing, but also some pretty core R&D. So hopefully, maybe that's one way of saying, hopefully I hope we don't have to choose between, heating people's homes and people developing, cute videos on using AI's platform. So, but I think that's one area that we haven't yet talked a lot about, is that the opportunities for efficiencies or technology advancements in that front.
A lot of the growth in the electric demand is we did get a lot of efficiency improvements over the years. Like you look at lighting, you think, yeah, we all have LED lights now. And it's like, we have a lot of light, but we're not gonna get it more efficient because it's sort of where it's pretty close to as efficient as we can get it. So in terms of allocating resources, you know, typically the economy allocates resources based on who will pay for what. And I don't think we're gonna change that. You know, people, I don't think we're gonna change that. You know, most people flew here, and if you wanna fly first class, it's like most people would, but not everybody's gonna pay the money to do that. I think we'll have enough electricity for people to heat their homes and things like that, but you know, individual people make decisions. It's like you know, do you heat with natural gas or do you heat with electricity? No.
Yeah, to add to that, I mean, I think it's a tough puzzle because, you know, right now where we are is the data centers are driving a lot of the load demand. They have a lot of money. They're moving very, very fast. And you know, my concern is we're entering the whole, you know, we don't have time to do it right, but we do have time to do it over type of mentality. And so in a lot of cases, you know, these data centers are moving into these towns and they're, you know, beefing up the infrastructure locally to be able to use the water from the facility. And then again, you know, to the point of the original question, taking that resource from those towns, but they're bringing a lot of money. In a lot of cases, they're modernizing systems from towns who have no money. So it's a problem. I think the key to it is what we're doing today is having these conversations and bringing folks to the table. You know, at least on the electricity side, we've started an initiative at EPRI working with the data center folks to actually try to incorporate their load profiles into grid planning, use their flexibility towards kind of minimizing their effects on the grid, and actually form a partnership. And so can we do that with the water side? Absolutely. Should we do it? Absolutely. To try to get out of this first to the party gets the water type of mentality and try to figure out, well, what's the best overall solution?
And a lot of state PUCs are looking out for the general consumer, and TVA is doing the same thing as far as the current rates are based on assets that have been primarily built and paid for in old money, so are fairly affordable. Any new piece of generation is going to cost more than something did 20 years ago. So making sure that incremental rate increase is borne by the new people to town is part of it. And then part of it is, at least for TVA, and I've seen other places also, making sure that while the grid is still trying to build out to catch up with the load, some of the new industrial loads have got to be dispatchable. They've got to be able to be shut off for a while. And so both of those kind of factors will help protect the general ratepayer as opposed to like bigger industrial payers.
Kurt, did you just say that new large industrial loads are paying higher prices than older?
Oftentimes, a lot of PUCs are kind of forcing that issue,
Okay.
right? Is that they don't want to see that their regular consumers are being taken advantage of.
Thanks.
I know Heather's got a question online. Maybe let's take one question from the room and then go to Heather, if there is one in the room. That's ready.
So Jordan, you presented some work that looked, I guess, at historical and future temperature and stream flow projections and how that might affect the performance of existing capacity. And then Brandon presented some that looked at a potential future capacity when you just don't consider temperatures or stream flow. And then you at the end of yours, I think, showed this new tool. I guess it's being developed by EPRI to sort of do some risk management for utilities that might be building new capacity to take into account some water-based risk. And then you brought up the idea of alternative water sources. I'm just trying to get a sense, and maybe this is a question for everybody and you're, to the extent that you interact with utilities who are doing the planning, at what point do they look at a new like capacity and then like decide to like how bad would it have to be given that the capacity events are pretty rare? Would they have to be to say, okay, I want to pursue an alternative water source?
I mean, I think that's gonna be up to each entity's risk tolerance and thoughts. I bet Kirk from EPRI would have some good insight in that from some of your members, but I mean, what we're seeing probably less people switching is if they are gonna be building a new facility, just starting, thinking about what are the long-term prospects for water security in that area, if they need to think about it, then that's when they might choose to utilize an alternative water resource as opposed to retrofit a system to bring in alternative water resources. But I don't know, Brandon or.
Yeah, I mean, I think that's the opportunity in this space, and I think part of why we're here is there's an opportunity amongst all this risk. I mean, Rick, I'm thinking about what you were talking about earlier and some of this produced water and the math you were able to do of what that cost is. You have to shut down a well and all of a sudden there's money you might be willing to spend, but you don't want to spend it all. Our industry needs to build new stuff. They don't want to spend it all. The industries aren't talking with each other, but the opportunity time is when you're building something new, which is, take something like cooling technologies, right? I mean, the power industries there's all kinds of new cooling technologies on the board, right? That could be put, it's just whether economically you could. But you don't really consider those when it's a sunk cost, something you've already built 20 years ago. It's this time when you're building all this new stuff that you consider this.
I can hit that one a little bit. One of the ones that you showed, pretty sure was one of TVA's nuclear plants, and we've shut that down. Once every few years, it'll shut down for a few days because the water temperature is too high. So in response to that, we upgraded our cooling towers. Now we're thinking about with climate change coming, water coming down the river is too hot to even start with, right? And it may shut us down 20 days a year. Well, that might be $40 or $50 million a year, right? So in that case, if we had to build a water pipeline from somebody or drill a bunch of wells or something, that might actually make sense.
Thanks.
Could I add a bit to that conversation? I didn't really talk about it when I was giving my presentation, but when we factor in what it's going to cost to recover some of this non-traditional water, right, and make it usable, there's a lot of factors that come into that cost of it. And one of those factors is return on investment for the capital invested in these projects. Well, if it's a smaller scale project and my company's going to go out and invest $10 or $20 million in it, I know our CEO, he's going to go, I want it all back in 3 years. Well, that means now all of a sudden I need to add $1 per barrel to the cost of that water to where I can get that money back in 3 years. But these larger scale projects, they're going to, especially for power generation and for data center, these aren't going to be short term. These are going to be long-lived, decade-long projects. So if we go out and as part of the process, we get dedicated funding for that the people that are funding it are willing to take 10 years or 20 years to get their money back at a guaranteed rate of return. Now, all of a sudden, that shrinks it down to where maybe I'm only adding 15 or 20 cents a barrel to the cost for the capital recovery on the project. And if that's the case, then that starts to make a lot of these projects. So it's going to be a joint effort between not only the water provider, the water treater, but also the consumer to try to structure these deals to get that cost concept down as low as possible.
Oh, can I chime in as well? So this whole data center conversation, I'm kind of living it right now with several small communities. So I'm very happy to hear the electricity side of this conversation because that hasn't hit the radar of the relatively small community where there's a very large data center coming in. Their water projections are almost 6 times what the current capacity is of the water system. Where they have chosen to locate, they would be discharged. It's once through cooling water because that's what works in their current model. The discharge is to an unnamed tributary, which is actually the bar ditch out front. And so they're talking about using 17 million gallons a day of water, discharging 17 million gallons. Just the construction is flooding the neighbor across the street. And their electric usage is, oh, they're just a customer who is connected to the system. So I don't know what you do with that, but that's what it looks like in small rural communities. That these issues are not even really part of the conversation.
With these data centers, it seems like that there's really a lot of short-sightedness going on with the siting of these things.
Yes.
In terms of, go where there's water, go where you might have natural gas to generate electricity. It just seems like, practical matter, and just, what's like one around Atlanta where they already have water scarcity and problems.
I'm gonna jump in. I think we need to jump to Heather because she's been waiting a long time. So Heather, could you ask your question?
Yeah, thank you. And this is more so on the previous thread around efficiency, and I really appreciate Jordan you bringing that in. I think there was some discussion around, well, we've made the improvements in lighting, but I do think as energy and water rates rise, the efficiency opportunity and needs will be even greater than they are. I just want to also point, the Pacific Institute has done some work specifically looking at water efficiency improvements in California, and the fact that if we fail to make those water efficiency improvements, that is then going to sort of hinder the state's ability to meet some of its sort of decarbonization goals, in part because it's this nexus whereby additional water would be needed. It would be these alternatives that are very energy intensive. And so it just points to, I think, the importance and the opportunity for water efficiency to be part of that conversation. And so I guess my question is, I wonder the extent to which other states, other regions are looking at sort of water efficiency as a strategy to save energy and take some of the pressure off this sort of energy water tension. So would appreciate any of the folks on the panel commenting on that, where they've seen that, or what they see are the opportunities there.
I could chime in maybe a little bit on that. As part of some of the work we're doing with DOE, we are characterizing different state level water plans, but most states don't actually have like a state water plan, and the ones that do, hopefully I'm not a bit naive, I guess, in terms of their estimates of potential new sources of water demands. Like they definitely don't have things like data centers on their radar. And I would say it's a little naive both on the energy side as well as on the water side. And so I think dug into I don't know, 23 or 24 different state water plans, but I haven't noticed, we haven't seen a huge amount of sophistication or like really like what I would say robust plans for like implementing water saving measures, or what do we do? And I think so many of the states, especially states out west, are able to rely on agricultural lands transitioning out of production and sort of buy and dry activities that might happen for new residential or industrial needs. I think that's a crutch that a lot of them are relying on. But I would be happy to share more as we sort of further navigate through like what's included in all these state level water plans. And the state water plans like do involve people from multiple sectors coming together, oftentimes for multiple months or years at a time, to jointly develop this. But there's not a lot of details, or maybe that indicates sort of the level of agreement on specific policy programs is not that great among those different parties.
Well, and just to add to that, I mean, and some of the reason why we did some of the modeling that we did excluding water was because in a lot of cases there's this mindset of it's not a concern until it's a problem. And so we've seen that where a lot of different regions, they're like, oh, well, we don't have that problem here. Well, you know, you get a modeling and then you look at our industry and see a 5x, you know, increase in consumption, you know, that's a huge problem. The other part is that, you know, we wanted to fight against this misconception that, you know, our industry as it modernizes was the water demand was going to go down because that has been the trend. But, you know, a lot of cases you get caught in that withdrawal versus consumption kind of conundrum where, yeah, withdrawal is going down, but consumption is actually either maintaining or going up. And the reason I say that and going back to the previous question to weigh in there is, you know, water tends to be very regional. You know, people think in a watershed, they think of different sites, they think of different water bodies. But there's a lot of solutions to your point where work in California can be transferred and lessons learned into areas in Georgia and the Southeast and other places because the chemistry is still the same, right? But we tend to think, well, I'm just in my watershed, I'm out in the Southwest, that doesn't impact folks in the Southeast. But what we've seen, you know, at EPRI talking to our members, there is a lot of lessons learned that can be bridged across the different regions, and developing those suite of options. I need to know what levers I have to pull. We can really build kind of a database that people aren't starting from scratch because generally, if you're developing a power plant from scratch, you take a standard reference approach that assumes you can take water from a water body or a groundwater well or something like that. And you just go down that road and you never even think of alternative waters and efficiencies of waters and things like that.
A good point for your committee with the grid is the water issues are probably more severe. We can build transmission and we move power. And I get it that people don't want transmission lines in their backyard, and I understand that. But if somebody says, I'm gonna put in a data center here, can you get electricity to it? It's like, yeah, we can get electricity to it. We know how to build transmission lines, and that's what we do. So it's easier, as I said, I mean, electricity moves fast and it's inertialess. I mean, there's inertia in the grid, but the electricity itself, we can move it a long distance. And this is something in Texas, we just decided as a state to build a 765 kV transmission grid, at least in the west part of the state. And that's gonna move a lot of power around.
I think that's a good point of that interplay of moving water and moving electrons, because you think about whether it's the power plant itself or a data center or whatever, and you make that decision of, well, I'm gonna reduce that consumptive water use and put in a dry cooling system that's gonna make that site require and need more electrons, right? And so that question of, well, what's a better trade-off for that site? Is it easier to get those extra electrons there? Because you're really just causing a interbasin transfer of water over the wires in a sense by moving where you need to get the electricity from versus where the water needs are.
Each of those things is a network. I would add gas and oil to those networks, right? So if you could think ahead and give a forecast of various price differentials in regions, people can invest in pipelines or transmission lines or whatever in order to solve optimally, right?
And it may be that your committee looks at, you know, the trade-off between with moving electricity, we're sort of moving virtual water around in a sense that, you know, I mean, if your data center doesn't have to do this one through cooling, which seems really strange to me, but it's like what you were saying. Well, right, it's like, I get it, it's cheaper, but maybe it's better if you have to build the data center there that you build the electricity and use a technology that doesn't use as much water. I mean, that's the trade-off, and that's where one of your projects could be looking at this.
I know Eric has a comment.
So I think a really interesting challenge to us is the differences in market. So the power grid and power in general has a very different market than water. I'll give you an example. So I presented at this Water and Energy Law Conference, And the group that's behind Bitcoin mining in the state of Texas, which is, I would maybe say e-currency is as big or bigger than data centers in terms of power usage. But in that market, the e-currency Bitcoin mining operations bought a tremendous amount of power from ERCOT in capacity. But they've leveraged the fact that they can sell back power in moments of demand need at a higher rate. We don't have anything like that in the water space. You don't have a carrot stick approach. You have a more of a stick approach. You use more water, you pay more. Here, you can kind of pre-buy in the market capacity and then sell it back at a premium. And they've advanced their expansion of e-currency mining operations in really significant ways by leveraging that market and the conditions that it plays in. That's very, very different than the way water markets work. So you can go to our TXPWC website if you're interested in a water market analysis. Westwater did for us, or the region in the Permian, and the value of water that's available in that region, and look at how that kind of plays out in this regard. But I don't know of anybody that's working on that kind of economic model in the water space that leverages that kind of future forecast capacity to buy and sell at a premium to basically leverage ahead. I think about our local water utilities and the fact that they plan ahead, but they buy in at a fixed capacity for some future demand that they're forecasting, right? And then they're stuck when you get into a drought situation and people use a lot less water. All of a sudden, they're not being able to pay their monthly payment for whatever that loan was that they've made to install that infrastructure in the first place. So then they start, tamping back the public announcements on conserve water, conserve water, conserve water, because they're trying to get to a price point that balances out the economics there. So while I would say it would be great if we could become more efficient and conserve a bunch more water, yes, but we didn't build the water infrastructure system around that kind of economic potential or capacity. So the water market is going to have to change, it seems like, if we're going to get to a place where we can start to think about an energy water nexus that's kind of on par with each other economically.
I think I'd like to jump in on that specific thing, having had 23 years as a water manager. Really there isn't a water market in the same way that there's an energy market. And of course, there isn't just one energy market either. But when we look at the overlapping jurisdictions and institutions and water supplies just in the state of Arizona, we literally have thousands of water companies. We have 5 or 6 different kinds of water. Some of it's leased and some of it's reused water and some of it's, groundwater and some of it's surface water. And in many cases, those are overlapping across the same jurisdiction, but they're controlled completely differently by the way the legal system works. And so somebody from the outside can do an analysis about what, you could theoretically do with a marketing system in water. And the reality is there is no water marketing system. People do buy agricultural land for the water rights, or they, speculate on water rights. But it's very different from actually buying electrons or gallons of water the way you do. So, okay. How are we doing?
I think we've got 3 minutes. It looks like.
Okay, 3 minutes. Okay, better be a good question. This has been fabulous. There must be another great question out here. Or another.
I guess I've got one. It's kind of a hard pivot from the current discussion. But one of the emerging trends that we've been discussing as a committee related to these water energy nexus conditions is wildfires. And that I'm wondering if the speakers can give us a little bit more perspective on what that means and kind of disentangling this water energy connection. I'm looking at you, Tom, because I know you've done some work with transmission distribution and wildfires, or at least know people who have.
Well, Don Russell's done a lot of work on that, and the electric grid does start wildfires. And most of them are at the distribution level, and there are devices you can put out there that can help reduce the risk of wildfires. And if I were Don Russell, I could tell you a lot about this.
But you're Tom Overby, and from the perspective of your statement of we can build more transmission, we could presumably also build more distribution. do we find ourselves in a situation where we're making one thing worse that sends it down this downward spiral when it comes to increasing wildfire risk in some locations?
I don't think transmission, you guys might know, but I don't think transmission creates many wildfires just because the trees are further away. I mean, they certainly can touch the lines, but they're less likely. The distribution is more likely. That would be my takeaway.
I mean, that goes trade-offs with anything. I think what we're also seeing is just building transmission, maybe Texas is different where you can do a lot more in Texas, but in so many other parts of the country, I mean, building new transmission is so hard. Because just the NIMBYism of it and dealing with so many different landowners on it.
It's become the limiting factor in us getting, it used to be building the plant, the generation plant, it's now getting the transmission.
Well,
Agreed.
thank you. Oh yeah, Brandon, if you want to take us home.
Yeah, no, I was just agreeing with that. Definitely not a wildfire expert, but I know, at EPRI, we are covering wildfires from about every angle, prevention, ignition, load, climate change, climate resilience. It's a huge issue for our industry. Certainly water factors into that. Again, it calls for the need and the challenge, like I said in my presentation, that's facing our industry. We have to look at it, as holistically as we can and try to factor in all of these, impacts and try to make the best possible decision that we can, and hope that we're not in that situation where we do have the time to do it right and we're not doing it over later on. And again, that's the fear here in the short term.
Thank you so much to our speakers, a very well coordinated panel.
Great job.
Yeah.
But yeah, so thanks for session 2, and I think everyone's gonna be around.
Good. Yes, that was fabulous. One more round for all of you. So, anyway, thank you. Not to mention that you all have a lot of smart ideas that we don't have. So, I'm not sure which group is ready to go. Is group 1 ready to go?
Group 1 is ready to go.
Okay. All right, well, let's hear a pretty short, high-level synopsis of the interesting things that we have to say.
So, group 1's pilot solution idea is a framework and demonstration project on siting considerations with replicable outcomes to co-locate data centers, water supply, correct geology for CO2 sequestration, power production, and water management. Our geographic location, it would be the Gulf Coast Basin, because it tends to have all of those things. Key technologies could include innovative CO2 capture technologies, which still need to be continued to be developed, but also the novel deployment of existing technologies. So matching up existing technologies that hit all of these components that we listed. We've stuck with the proposed 50 million per year for 5 years. I think that would do that. The potential partners or sectors that could be involved would include data centers, public utilities, class 6 operators, environmental consultants, venture capital, because we're seeing a lot of that in the class 6 realm, finance expertise for these large scale type of projects, state government that has subsurface expertise, that's several different agencies, including geologic surveys, the oil and gas industry, monitoring and verification expertise, regional planning and water planning agencies, and then the state regulatory agencies where you would acquire permits. And then the initial idea is that this framework considers having all these different components, like I mentioned, the co-location of data center, water supply, etc. But for a pilot solution idea number 2, we determined that there could be a location where 1 or 2 of those components already existed. So the transferable knowledge would be how to then bring in the additional components. So if you already had a good water supply near your power generation, but you wanted to bring in some of these other components. So that's our idea in a nutshell.
Great. Any questions on that? All right, thank you for your report. All right, group 2.
Kurt, thanks. We are talking about the Pecos Valley Sweet Salty, multi-scale, multi-sector, multi-use project. It will involve industrial water, brackish waters, and a variety set of source waters. It'll involve industry partners that would include data centers, agriculture, land restoration, regeneration kind of effects. It would be located somewhere south of the probably Texas, New Mexico border for permitting issues near Orla, Texas, south of Carlsbad. It would involve key technologies in desal, technologies in power gen that would include gas, nuclear, and renewables, wind and solar primarily. It would involve large-scale monitoring of both volume and quality, include new technologies and things like membranes and bipolar membranes. Scale-wise, we're looking at a scale of desal systems that would be in the 10 to 50,000 barrel per day systems. That could also look at brackish, zero liquid discharge and blended produced water scenarios. We would be talking probably about a budget that would be $100 million a year for 5 years, 500 million total. And we would consider that a $500 million public, $500 million private match. The partners obviously would involve the major grids, ERCOT, the Western Grid, all of the environmental agencies, NMED, TCEQ, EPA, PEDAL, that's kind of emerging in Midland, all of the regional kind of institutions that are involved, the university lands from the UT, Texas A&M system, NGOs. We have building relationships with all the groundwater management districts, irrigation, power districts in the region. From a metrics perspective, we would think about water quality, economic viability, sequestration. There's a Oxy's direct capture plant is very close by. So we could look at that. There's also another sequestration project that's on the New Mexico side of the border that's involved in the same system that's tied to future natural gas gen. Reduce risk at scale and reduced uncertainty at scale would be what we were after, along with critical minerals. And then minerals that aren't critical minerals, but could be very valuable and reduce kind of production and transportation costs that would involve things that are in chemistries right now used in oil and gas production as a whole. Things like, and then ammonia for things like fertilizers that are used in the region as well. Did I capture everything correctly, Pete?
That is a giant pile of stuff. Yeah. Okay, wow. All right, yay, group 2. All right, group 3.
Do you want me to? Oh, okay, I guess I'll do it. Okay. So group 3 was this net zero community idea and sort of how to understand the future limitations of a specific place. And so we had a bit of a philosophical discussion. First of all, over, I don't know, we debated why it was even advantageous to have a net zero community specifically. And then when we were thinking about proposing solutions, those solutions really just became places because intrinsically you're thinking about very specific locality for this topic. So we started thinking a little bit about Oklahoma as our place, but then we drifted into a conversation about, you know, what would actually be helpful for small communities to help them, you know, understand their specific limitations and what information do they not have and what information do they need. So the key technologies that we kind of landed on, which maybe is ultimately the idea and not the technology, is the development of a tool that will help a community do a techno-economic assessment of what they have. And in terms of potential partners, we've talked about organizations of localities like National League of Cities, Governors Associations, Chambers of Commerce, and then of course, utilities, power companies, water planners, folks doing research in academia, and also potentially like tech industry, because they could maybe help with the development of these tools. So the technology may actually end up being, you know, like computing and AI.
Great.
And anybody else, if anyone wants to add to that, I don't know. That was my interpretation.
All right.
And originally, we came up with the concept rather than 3 separate projects, or we would have 3 different locations that we would use to evaluate this tool. One would be West Texas, one would be here in Oklahoma, since we're here in Oklahoma, and another one would be up in the northern Midwest, like Minneapolis, St. Paul, or somewhere up in that area, because we got 3 huge differences in geographies and availability of water and availability of energy. And that's the whole purpose of the tool, is if you have a city stand up and go, the city leaders go, we're gonna get a data center in here. Here's a tool that's gonna help you decide what it's gonna cost to do that, and if it's even practical, you can do it.
Great. All right. Group 4.
Okay, so I'm gonna be, I'm group 4, right? We're gonna be representing the online group 4. And so we were focused in on real-time monitoring of produced water discharges and water quality. So in terms of the issue to address, we're addressing sort of excess produced water with real limits on discharge. Geographic location, we sort of interpreted this a little bit differently, but close proximity to areas where produced water is being generated. But we also sort of thought of the application of this in other geographies where there's produced water. So not only in Oklahoma, Texas, New Mexico, those are obviously some of the geographies we heard about, but California, Pennsylvania, just other regions. A number of other regions are sort of grappling with produced water issues. The other thing we talked a little bit about were opportunities to broaden, right? This needn't just be about produced water. It could be brackish water, brine discharges associated with water reuse systems. So there's some diverse geographies. In terms of the technologies, we identified a couple of key technologies, sensors, telemetry, data management system. We are also interested in exploring opportunities for using remotely sensed data as a proxy and testing that out. And then in addition, there need to be sort of alarm systems developed as well. And the idea of monitoring not only the produced water or the treated produced water, but also the receiving water body. In terms of the budget, we actually thought the cost would be relatively modest for this, generally in the $4 to $5 million per year. We were envisioning sort of multiple sites that would help to include more variability with respect to the quality of the water. We were also, again, talked about the opportunity to add in the remote sense technology, which would add on a little bit of additional cost there. In terms of partners, we identified there'd be technology partners, oil and gas operators, state agencies and regulators, academia, universities, and then community or NGO groups. And that would depend on kind of where the discharge is happening, but the need to sort of include some of those folks who might have concerns about that discharge. I'll just also note, we had a little extra time, so we were really interested in doing the net zero water energy community as well. I love the idea of a tool. We really jumped in on the technology, and we're thinking of sort of a rural area where we could do a pilot. And we're focused in on solar energy and storage opportunities, as well as recycled water, gray water, rainwater systems, and efficiency. So happy to share that. I could go on, but I'll I'll let us get to other things in the agenda.
Great. Thank you very much, Heather. Appreciate it. Okay, well, let's give ourselves a round of applause here.